Alright. I started this one late. There was a lot going on. Anybody that does not know, and you may not know if you're not in America, but there's been this big thing going on what called the Epstein files, and they just got released, and there's a lot of stuff going on about the president being part of the Epstein files. And
pages have been redacted.
yeah, there's pages that, hey, what's up, Black Cat Man? There's whole pages that I know. I finally got to 200. I was like, I didn't even notice. I think I hit 200 like after I got off or something. I don't know, but hey, what's up, Milton? But yeah, I was gonna try to start earlier, but I'm starting later because I got my friend to sub to you. Oh, is that how I got the 200? I appreciate it. Yeah. But yeah, I was gonna start this earlier, but I've been kind of watching the news because all that crazy stuff's been going on, and I don't know what's gonna happen. But I don't even know where everybody else is with that. But it's just some crazy stuff going on in the country right now. But yeah. So, and then I found out that I guess somehow I skipped some of these. So, yeah, I'm trying to make sure I actually get all this done in order. I don't know how. I guess I skipped this exercise somehow. I don't remember. Do you have the game geometry dash?
Yeah.
Oh, my son plays that all the time. I know what you're talking about. But yeah, my son plays that. It's like his favorite game. He even plays like all the songs. Hey, what's up, dude? Code 4K. Yeah, he loves that game. He loves that game so much, like he'll play it, and then on our Alexa, he'll sit there and he'll play all the songs that are on that. He'll just tell her to play the Geometry Dash songs. So, yeah. So yeah, I'm basically trying to get back to this, trying to lock in on it. I don't know, all that stuff that's going on in the world right now is crazy. So that kind of distracted me this morning, but I don't know. I don't know if I should go back and see the video for this because look, I got like way far in this, and then I didn't realize that I skipped this one and I skipped that one somehow. So, oh, finger. Okay. Consider the following code. That's a lot of stuff. If this code is executed, it will print that. Succeed or succeed. Remember floating points errors. Now suppose we try the following. Select the answer that best describes what occurs when the above code is executed.
Okay.
Okay. I know I haven't been playing games as much ever since I started trying to lock in on this stuff. I kind of got like a time frame where I need to like study this as much as I can before I don't have the free time too. So,
Okay. Well, I could definitely tell you now that the other one is going to take a lot.
Oh, okay. Now I remember doing this. This is when
that would be half undone.
you would, I believe, yeah. This was like, let me think. Yeah, I think it was like you put it in a loop until it runs so many times. Let me see. What was this called?
Tattoos.
Oh. Let's see. Approximate solutions. Could have swore I made one for this. Screw it. I'll put this in here real quick. Wait, if absolute guess to the second power is less than x, or take away x is greater or equal to epsilon. Oh, yeah, that's right. That's right. Okay, so like, are you going to play or do some coding? I gotta lock in on this coding stuff. I only got so much time to. I got basically a deadline where I gotta try to learn all this stuff as fast as possible. So I'm probably gonna be doing. Yeah, unless you come through. Yeah, unless something else happens. There's a lot going on in my world right now, so But yeah, so I'm trying to get this down as much as possible. I'll probably still be able to play games every now and then, but I'm gonna be trying to get this down as quickly as possible, as much as possible. Um,
Cold outside. Yeah.
huh?
So it's gonna be cold outside.
Cold
Yay.
outside. Uh, so I remember what this was. This is approximate solutions, and all this does is you start with a number, and you create a way for this to guess the closest number. And so basically, this is what it's saying is, yeah, if you pass the number, then it failed. That's right. It was finding the square root. Yeah, it was finding the square root of something. And if you pass the number, then you obviously failed because it's way too big. Else you would put succeeded and then type it out. But you would put it in a loop where it continuously add guess by step. So you start with 0 and you add 0.1 until you're this close to what the true answer is. Now the only problem with this is depending on what number you use, sometimes you have to add a 0. So that was the only thing, because that's what it's saying is like if it succeeds, then you could get a number. If it failed, it's because it passed the number. Because this is what you're saying, you can come this close within the true answer. So, um, the square root of 25 is 5. So, well, it's 0.01 and 0.1. I mean, this is the same one as this one. If this code is executable. Is that one any different than this one? I don't even see a difference. Oh, they changed this else. Okay. So they got rid of the else. Okay, it up. Yeah, this one changed here, so there's no else for the if. So all it's gonna do is do this. It has no break, so it's gonna be error. Script successfully completes what prints out failed script. And yeah, it's an infinite loop because it doesn't have a break. Okay, now suppose we try this. This one does have a break, else break. Okay, wow, absolute guess. Let's see, what does this one look like? Absolute guess. So, your guess squared, take away x is greater or equal to this number. If guess is less than or equal to x, guess plus equal step, else break. Okay. So once it passes, once guess is bigger than x, it'll break. If absolute guess take away x is greater or equal to epsilon print failed, else break succeeding. I think that should work. I'm pretty sure. That looks like it would work. I don't really see any issues with this one. Is it? I don't. Well, no, because wait. Greater than or equal to, then it's going to add. That should work. I'm pretty sure. Followed by some number not really close to 5. I think that one works. Finally, let's use the same code as immediately above, but change the first line to 23. Note that the square root of 23 is roughly 4.0, so it's not going to. Yeah. Well, it's what does it do if it doesn't? It's gonna go to. It's gonna fail because it's gonna pass up the number. I thought. Okay. Yeah, I got it all right. Okay, cool. See, I'm learning stuff. Look at that. This was like, what, the other day? 2 days ago or something? And I got them all right. Bisection church. I just did this the other day, didn't I? Oh, yeah. I already did this. Why does it say I didn't do this? Is this it? It's just this? Ugh. I think it wouldn't let me do it because I did this. Yeah, because it's not letting me do anything. Yeah, this was like a thing where it just found a way to. All this is it shows how coding works in a visual sense. Whenever you make a code that's trying to find something, let's say you select a random number or letter and it's V, then it'll cut down part of it and cut down part of it and keep cutting down part of it till it gets to it. But depending on what letter it is, it can take more turns before it reaches it. So, I don't know because I need this to check. So I guess I gotta put all these as neutral, which is kind of annoying. I mean, it says not to worry about it, but it's not giving me a check unless I do that. So I'm just like, alright, back to where I was at, right here. Alright. I'm trying. Alright, estimated time of the late 18 minutes. So we can use the idea of bisection search to determine if a character is in a string so long as the character is sorted in alphabetical order. Oh yeah, I did the alphabet thing the other day. Where's that at? Oh, here it is, alphabet search. Let's see. I have to create a code. Test the middle character of the string. Okay.
Someone is at front door.
No. First, test the middle character of a string against the character you're looking for. The test character. If they are the same, test the middle character of the string against the character you're looking for.
Oh, baby. I mean, you can ask, but I'm pretty sure they have plans, kiddo.
What?
Just say hi. Say hi.
Say hi.
Tell you know what is it?
What?
What is it?
What is it?
What is it? Sit.
I don't know.
What is it?
Sit.
What is it, Baba?
Baba?
No, the front door.
Oh, the front door?
Yes,
You gonna go say hi?
yes.
Go say hi.
No, you say
You want me to say hi?
yes.
Okay. real quick.
It's the original vanilla, not the Rocky Road. I like that. This is really well done. She got featured in a gallery space, and she just won the top award for the pickle. Yeah, it was awesome. She's got the recipe still.
I'm making a cookbook. That's why it says cookbook.
Yes, I
It's a
bet.
little, but it's a bit hard to see because it's really colorful.
And then Cora has now delved into cooking, so
Oh,
she's making her own cookbook.
stop.
Yes.
I made a cookbook too.
Oh, very nice. Very
The
good
words,
job.
the words a bit hard to see because it's very colorful.
You want ice cream?
I want ice cream.
Okay, then stop. Well, okay. I'm gonna leave this here. I'm gonna go ahead and turn off the stream because
This time it
I'll
should
be back. I have people here, so it's gonna take a second. I don't know if anybody's still there, but. Alright, it's back on. Well, sorry for anybody that had people come over so I had to get off. Okay. Back to what I was doing. Let's see. Where was I at? Which one's this one? This one. Okay. God dang it, now I gotta remember what was going on. I don't know why I kept your tab. No. I didn't even, I can't even tell if you're on there. It's showing that no one's on there right now, so I didn't even know. Yeah, I had to go for a second, but, yeah, let someone come over, so I had to stop, but, alright, I gotta get back to where I was. So this had something to do with, I guess, the alphabet thing that I did last time. Oh, yeah. What? Okay, yeah, this was the test, and this coding was just designed to... yeah, he created this code just to find out the longest string and the longest alphabetical string within a string. So, but that's what all this coding was for. And I guess this is yeah. Oh yeah, here it shows. Yeah, that's the string and that's the result. So I guess I gotta find a way to make this useful for this. God dang it. Well, how do you do it? Because I already forgot. Like the what? So the initial point was If not okay, so there's only one function. Okay, no, I didn't create this myself. This is one that he created in the video. And I could go back and I should probably go back and rewatch the video, but all he did was the instructor. There. Let's see. There, I can rewatch it because that was like last night.
We've seen a number of examples of recursive functions, something you're going to use a lot. But all of them so far have just been numerical. So let me show you one more example that I can do recursive problem-solving recursive functions on other things, for example, on strings. So here's the challenge. How would I tell if a string of characters is a palindrome, meaning that it reads the same forwards and backwards? Now I'm going to cheat a little bit and remove punctuation
Not the alphabet, those are the
but I just
palindrome
want to
things.
know, is something a palindrome? Probably one of the most famous, attributed to Napoleon, although I don't know that he said it in English.
Oh, no, that's not the alphabet one. That's not what the last one was. It was... Hold on, I got it. Where was it? This one. Okay, so he used a way... he created this, and all it basically did was it would take a string. So like, I guess if I'm using a string input, like that one's the small one, for example, and it takes the first letter and the last letter and sees if they're the same value, and if they are, then it deletes it, and then it goes to the next first and last, and it checks if they are the same, and if they are, then it deletes it, and it keeps doing that and checking the next one and checking the next one until you run into just one letter left. And as long as all of those are equal, by the time you get to the very center letter, then it'll return true. Otherwise, if not, it'll return false, because if two aren't equal letters, then this is what he did. But like, see, it says Eve, and then there's also this one, and it's literally just like the same thing written backwards, that the palindrome thing. And if I run it, it'll say that, well, I mean, I got that text right there, but this true is for Eve because it's E and E, and then V's in the middle, obviously. And then this one's true because Abel and Elba and was, and, well, I mean, I don't remember exactly how it was spelled out in the word, but the letters are all backwards. And that's what it was doing, was it was like going down one by one from each end, comparing the two, and then it go down, compare those two, go down, compare those two, until you got to the center.
There I saw Elba. If you look at it frontwards or backwards,
the
exactly the same.
The instructor came up with the formula. So whenever he comes up with a formula, I also type it in here so I can, well, I got to practice my typing, but also to get an understanding of how it works, and to save it, so if I need to come back to it, then I can look at it.
Second one,
But
attributed
that was one that he created, not me.
Dan Michaels. Are we not drawn onward? We few, drawn onward to a new era. And you can see if I read it from right to left or left to right, it's exactly the same. I'd like to write a piece of code that can solve this recursively. And you can think about doing it
Yeah, see, Abel was I, error, I saw Elba.
So how would I do it?
Backwards.
Well, I'm going to do a
Same
little
thing.
bit of cleanup first. I'm going to convert the string to just the characters. I'm going to strip out any punctuation, and I'm going to convert lowercase, or everything from uppercase down to lowercase. So I just have it all as a sequence of characters. And then I've got a very simple solution. If the string is empty, it's a palindrome. If it's just of length 1, it's a palindrome. Otherwise, how would I tell if some string is a palindrome? Well, check the first and last element. If they're the same, then check everything in between to see if it's a palindrome. That's cool. That's a recursive solution. I've just broken it into a simpler version of the same problem. And of course, as I keep breaking it down, eventually I'm going to get down to either a string of 0, if the whole thing started off as even, or a string of 1, if the whole thing started off with an odd length. Can I do that? You bet. I'm simply going to write a little piece of code that's going to say, if I've got a piece of code that's called is palindrome, I'll first convert this just into the string. I strip out all the separate spaces, the punctuation. I remove uppercase to lowercase. And then, as I said, if the first and last element are the same, then I just want to check, is that a palindrome? And there's the code. Nice and compact, nice and simple. I'm not going to walk through all of it, but you can see the first part here is simply something that's going to convert that string into characters. It takes advantage of a property of strings that I can call a method called lower that will convert everything into lowercase. And then I've just got a nice little iterative loop here that basically walks through each character in the string. There's that iteration over the string itself. It's a string iteration.
Can't even
And it
read
basically
that.
says if that character is, in fact, a character, add it in. And then there's that nice, elegant solution to palindromes. It says given one of those strings, if it's of length 0 or less, if it's of length 1 or less, it is a palindrome, return true. Otherwise, check the first and last. There's that call with -1 to a string, the first and last character of the string. And check by slicing out from the string everything but the first and last character and see if that's true. And finally, I'll just convert the string and call isPal on it. Let's try it out. I've got those two characterizations over here. I've got it loaded up, and if I call it, it says, is, for example, a simple thing like Eve a palindrome? You bet. EVE is a palindrome. And what about is Abel, was I, ere I saw Elba a palindrome? You bet. Again, notice how thinking about it recursively has let me find a really nice solution to this problem. This is a very crisp piece of code that solves what otherwise seems like a very hard problem. Could you solve it iteratively? Sure. But you'd have to keep track of where you are on both ends of the palindrome as you decrement them to walk in. That sounds like a pain. I'd much rather think of this recursively, and that's what I did. This is...
So I'm kind of confused with the loop. So it's a recursive function. So I guess this is the part that it's going to take away the first and last, because it says if the first and last are equal, let's say S0 would be the first one, equals S-1 would be the last one. Yeah, return if those are equal, and ask me if you got any confusion in that code. When you read the code, it feels like you could do it, but we couldn't do it ourselves. Hey, you can't say we couldn't do it ourselves, because if we sat here for a couple of hours, honestly, we would probably be able to get there. We just sat here like hardcore thinking about it. But okay, this is what it is. Yeah, okay, here's the loop right here. All this is to, get all the characters out, take the spaces out, take the commas out, all that stuff. This is just to clean it up. This is the real function though. And this is okay, basically like if it's equal or less than 1, then it's true, because the only way this function could continue is if these were true, not false, and which it would return false. So yeah, I guess this is the only thing, because it's calling it. Okay, so this is saying first, if the first and last letter are equal to each other, then you got the ands. So in addition to that, if this case is true, then you're also going to rerun this function, but you're gonna single out the next two. So that's gonna be you're going to run this function again as the next one right here. But that says -1. So -1, wouldn't it be A? If S equals... Let me see. I need to double check this real quick. Because if this is -1, then this is, I mean, that's obvious. You're checking the A here and the A here. But if this is 1, then you're skipping past A and you're selecting B. And this is -1, so you're selecting A. But I guess if it's -1, then you stop before that point, maybe? Is that what it's saying? I don't know why. This is kind of... Here it is. Let me do this. I'm going to test it. Because I thought it selected the last number. Let's do S equals... Okay, and call S, okay. And then we'll do S 1 and -1. Oh yeah, it does. Okay. So it does work correctly. That is weird that it does that. So if you put S and you're selecting -1, if you just select -1, then it gets the A. But if you do 1 and -1, then it... Okay, that's kind of weird the way it does that. But anyways, but that's how it works. It's a pal if it's greater or equal to 1 else. Check it. Yeah. Yeah, so it gets stuck in this loop of this calling its own function right here, and then it continuously checks to see if the first and last ones are equal, while it's only selecting the next set of inside letters. And then it keeps running that until you get to this point and it'll return true. And if it doesn't get to this point and return true, or these aren't equal, then it returns false. So, I mean, it's not like, yeah, it's not too crazy complicating or nothing, so. I mean, I don't know. I say that, but like a lot of the times when you're looking at this stuff, what if you do 0 and -1? 0 and -1 on, if you do 0 and -1, then it won't take out the A and B, and it'll be the A in the front and the B in the back. So that's all. Like if you were to do it 0 and then -1, then yeah, you would it wouldn't take it out evenly is all. So that's why he has to put the 1 here. But he has to put the 0 because you're selecting that number. If you put the 1, you're starting from that number. But the way they do -1 and -1, -1 selecting the number, but then on this side, -1 stops right before that number. I thought that was kind of weird the way it does that. But because here it's like you're selecting this number because it's in the front. But when you put it at the ends, then it doesn't show that number. It stops before that number. I don't know. I thought that was it was different, but.
And that sounds like a pain. I'd much rather think of this recursively, and that's what I did.
Okay, so now I have to figure out a way to do it myself for this problem. Is, okay, we can use the idea of bisection search to determine if a character is in a string, so long as the string is sorted in alphabetical order. What? We can use the idea of bisection search to determine if a character is in a string so long as the string is sorted in alphabetical order. First, test the middle character of a string against the character you're looking for the test character. If they are the same, we are done. We found the character we're looking for. If they're not the same, check if the test character is smaller than the middle character. If so, we need only consider the lower half of the string. Otherwise, okay, so this is looking at it like we're using characters, like alphabetical characters, but you could be, it would kind of be simpler to take this logic into like integers, like using numbers. But basically, what they're saying is that so he's got a string of alphabetical orders. He's got a string of like the alphabet basically, but he wants to see if he it's like basically you have a string of the alphabet and he's trying to find a letter, and he wants you to be able to start from the middle and then see if that number is too great or too small, and depending on what it is, then you move in that direction. It's kind of like that other, we were doing another one just like that wasn't, but it was like with numbers, like the number finding thing. There was a number finding thing that we did where it was like, you know, between 1 and 10, or yeah, the 1 and 100, it would try to guess your number and it'd start from the middle and keep working its way down. This is the same thing, but instead of using characters instead of uh, numbers. So, let's see. We can use the idea. How would we first test the? Okay, hold on. Let me see what all this says. I got a note that you can compare characters using Python's. Okay, implement the function which implements the above idea recursively to test if character is in a string. Character will be a single character, and a string will be a string that is in alphabetical order. Okay, wait. Okay, so the character, which implements the idea of recursively to test if the character is in the string. Okay, so you want to see, this is a single character. This is basically the alphabet, and you want to see if this character is in here. It wants to use a recursive function, so it wants me to create a function within itself, a recursive function. The function should return a Boolean value. As you design the function, think very carefully about what the base cases should be. Well, I mean, I guess I could do that stuff where he made sure they're all lowercase and stuff. I mean, this doesn't look far from what he was using, except he was checking the outside characters. So instead of checking the outside characters, I need to find a way to make it where it checks in the middle. But no, okay, but I already have a character I'm searching for. So I don't know if it's telling me. I have to be super careful and make sure the string is all lowercase. No, in programming there are many ways to solve a problem for your code to correct, though you must write your recursive function such that you make a recursive call directly to the function is in for. Thank you for your understanding. When you already made it. Is in. Okay, so I need to do something along the lines of the strings, the alphabet. Can we use a for loop? Yeah, we can. I mean, that's what he did here. It's fine to use a for loop, but it's not recursive if I only use a for loop. It's only recursive if I use the function within itself to create a loop. So, and right here, the recursive function is this one right here. This is the recursive function because it's using this within itself and it causes a loop.
Dada,
What?
go on my pick up. Go on play game.
Oh, you need to pick toys up.
No, cool. I want to buy this. Cool, I want to pick it up. That. See, come.
Okay, you need help? Okay. Wait, I'm gonna try to make that function. Yeah, you can go for it. Here, I'll be back in a second. Let's see what I can come up with. We did a number thing that was similar to this, but the difference was the number is 1 out of 100, so you already knew to start at 50. So I guess I gotta find a way to get a string and select the inside number, and then if that inside the very middle number, if that very middle number letter is not the correct letter, then I have to compare it to see if it's greater or less than. If it's less than, then I need to check all the way less than. If it's greater, then I need to check it all the way greater, and then you keep doing that until you run out of. Yeah. What? Okay, Olivia, come up. Pick up your toys. Maybe just leave that for now, because I'm trying to study. Always lengthy. Why not just check it from? Because that's what he wants to do. If you read it, it says first test the middle character of a string against the character you're looking for. Of the test character. That's how he wants to do it. Now, given, I don't think the system checks to see if you did it exactly the way he's wanting you to do it, but he's wanting to do it this way just to make it to where it's kind of like a teaching thing where it would be easier to do it a different way, but when you create another obstacle, it helps train your brain to find specifics in case, you know what I mean. No, he said it. I think it says it's already alphabetized. So here's the character you're looking for, and here's the alphabet. And he said, yeah, so long as the string is sorted in alphabetical order. Um, okay. Yeah, it says a string will be a string that is in alphabetical order. Right? Implement the function which implements the above idea recursively to test character will be a single character and string will be a string that is in alphabetical order. You know what? I don't know. Actually, now that I think about it, I might have to put it in alphabetical order. I thought that's what it said, was that it keeps it, but it says implement the function which implements the above idea, and a string will be a string that is in alphabetical order. So I think maybe crap. We'll see this a single character, and that's an alphabetized. I think the A string's supposed to already be alphabetized. I don't think he's making me alphabetize it, but And we can really compare alphabets using, huh? You can create like yeah, I think I was doing that the other day. Is that's how you search things in the alphabet. Like if we put A greater than B, it'll say false. Oh, I gotta make it a character. My bad. Hold on. Yeah. So the Python knows, and then look, for example, A less than. Oh, god dang it. B true. So the way that Python sees it as is A is the smallest, Z is the biggest. Yeah. So it can alphabetize. I think he was saying that it's already alpha. I think it's saying right here that it's already alphabetized. I kind of hope so because that's like a lot of extra coding to also additionally put. So I'm hoping all we gotta do is do the character where you start from the middle and then work your way down one way or the other. Let me see. I'm sorry, I got a headache. I don't know how many of these I'm supposed to take. Like 1, 2. I get headaches a lot. It sucks. Alright, so I can take 2. I'm gonna take 2. I hate headaches. Yeah. Alright. So, I first test the middle character of the string. So first, I don't know. Now it needs to be in a loop. So, I think for C and no wait. How do I select the middle number in the string though? I know how to select the first one. I know how to select the last one. I know how to skip. But if I, okay, so I need to figure out the length of the string first. Let's do like, let's see. Let's do, try a string. Or what is the length of a string, right? Length of string. Okay, dang it. A string. Is that how you do it? Okay. Length of a string. Make an integer for it. Call it half. Equals length of a string divided by 2. Alright. And then for character in string, and you're going to select the half number. Okay, for a character in a string, half. Let's see if. Okay, I think it's if equals. Oh wait, no. If character equals. If character equals a string, the half number, then return true, else return let's do this. No, wait, no. I don't think I need to do that. Hold on. You did it without doing the middle thing. Well, I can get the middle by doing this and then doing that. So, and then I just got to do the loop here. Then return is in, but well, no, because it needs two characters. Well, I guess this character just stays the same, obviously. And, but this one's gonna change a string. Oh no, I forgot the greater equal to. Hold on. Wait. I gotta do the greater equal to then. I forgot about that. I can't just search. Okay. If it's not. God, okay. Return true. Else. Then I gotta figure out which way I'm going with it. If it's greater than that number, then I need it to start but end at half. Okay. And then else. Man, I should have put this one. No, because that has to be first, right? Because it checks it first. If that's true, then it does this. And if that's not true, then I mean I could just put else. So that I shouldn't have any errors with it, hopefully. Then return is in. It starts with half, so I don't need to do that like that. Now, I think this should work. Now I'm gonna try this. Yeah, I think this should work, but I think I'm also like I didn't make it to where it doesn't do anything it shouldn't. Let me see. If there's an error with the input somewhere. Okay, I'm hoping that's already alphabetized. I don't want to have to do that. This should work. If it's equal to it, return true. Oh, or else, if it's greater than it, if this, I'm gonna do this right. If this character is greater, then I'm gonna return. I don't know. Let me see. If it's greater, no. God dang it. Greater. If the character is greater, then it's gonna be the top half of the screen. Your code cannot make use of the N keyword. I can't use the N keyword? What? Error? Invalid syntax, yeah, because I have to put in, but I can't put in? I can't use N. What if I do while? Will that work? Oh, that won't create a if. Dang, oh my god, your code must make a recursive call. This is the recursive call right here. When you already make a call to. Let's see. What's this saying? Oh, wait. Let me start using this. Let's see. Point 0.5. It only worked for something? What the It worked for this one. W and W because it found itself. What? Line 16. What do I do in line 16? There's nothing in line 16. Alright. Well, I think. String index out of range. Okay, half equals the length of the string divided by 2. Do I need to put this in parentheses? Divided by 2. I don't know what I'm doing wrong. I'm doing something wrong. found that because it's already in the middle. I wasn't able to find that. Return is in. It's because it took too many times. Output. I mean, but this is half of the string, right? Or is it? Well, this one doesn't work because there's nothing in this one. I mean, so this the correct output of this is false, but I don't. God dang it! Oh wait, does it put these in alphabetical order? Yeah, okay, they are in alphabetical order already. So I wasn't wrong about that. Oh, I didn't put anything if it's not in there. Oh my god. Okay, if it's equal to. I mean, does this really work? Do I need to put like a +1 or something? Let me see. Okay, let's say length of string divided by 2. So 7 should be the middle number because length of this is 14. So if you put Wait, so 7 is T. Does yours work? No, I did something wrong. Let's see. Well, first off, I did this wrong. Where is it? Oh, wait. Did I just put... Oh, no, put it on this side. Okay. Okay, so this is from the half to the end. Wait, oh, did I do these backwards, actually? Wait, if it's greater... If the letter's greater... Then, crap, I think I did this backwards. Stuff gets confusing. Hold on. Okay. If the letter's greater, that means it's a lower number. So, yeah, I think I had that backwards. Oh, let's see if this works. Three out of 5. No, because I don't have none for this one. Hold on. Okay, so it worked for this one. It worked to find the S. It didn't work for G because G's not in there. But I put else. Return false. And if it's greater, that's... Oh, wait. If okay, so if G's A, B, C, D, E, F, G... I mean, if... Yeah, I didn't make it. If the letter doesn't exist in here, then I don't have anything saying that's false. So I made it to where it finds it. But I didn't make it to where, yeah, if the letter's not even in here, then it's just going to keep searching for it. Oh, crap. But I can't use the N, so I need to make it to where it keeps checking until it runs out of checks. So, okay, I think I got an idea. We have almost same code already. Yeah, so like I got it to find it, but I don't have it to where it works if the letter's not in it. That's my only problem. If the letter doesn't exist in it, then I don't have it a way to... It just keeps trying to find it. So what I need to do is I guess I need to set a limit. I'll do like count. I call it limit or something. That's what I need to do. I need to set a limit equals the length of the string limit equals length of string. Then do limit equals 1. And then I need to make it to where if the limit runs out, if limit's 0,
Mommy, Dada, Dada, Dada.
I hate doing all these LFs, but I don't really know another way to write this.
Dada.
What?
One toys. One toys. One toys. One toys. One toys. One toys.
I don't feel like this is the greatest, but
One toys.
oh, that didn't work for any of it.
Dada.
I just made it worse.
Dada.
What?
One toys.
Oh, you need to charge it?
Yeah.
Okay, I'll charge it for you. God dang it. What am I doing wrong? Oh crap, wait. No? Yeah, the limit's the length of the string. Why didn't that work? Oh, that worked. God dang it, that one. But now, why didn't this one? There's no P in there, so it should have broke it, right? Oh, I need to put this up. God dang it. Hold on. Oh my god, I'm making it worse. What am I doing? God. Oh, okay. Dang it. Come on. Oh my god. I got way too many LFs in here. Oh crap. That's off. What I do? It should return false if it runs out of tries. God dang it. Read the chat more. Oh, I'm sorry. Wait, what do we type there when we need it to tell it that if... No, you did it? Yeah, dude, I had it set up to where it was working. You know, it would check it, but it wouldn't find out if it's not there. Now I don't know what I'm doing wrong. Because, like, this is what I was thinking. I was like, all right, give it a limit. The limit is, you know, the length of the string. And limit take away 1 every time it goes through this function. Right? And then, yeah, I was like, if the limit is less than 0, then just return false. So that should stop it. Especially because it's up here. And now, I don't know why, but that just made it worse. Well, no, because it... Okay, yeah, it still finds it if it's in there. It's just... It's still not doing anything if it's not in there. And I don't really know why. Okay, it's in an infinite loop. But... Why isn't that working? That should work. I mean, because you take away... Your limit's the length of the string. And then limit take away 1. If limit reaches 0, then that should work. I nearly did the same thing. It worked. You're close. I don't know what I'm doing. That, like, how does that not work? If limit's less than 0. What about less or equal to 0? Is that why I'm... Let me try... Hold on. Let me try that one. I wonder if that's messing with it. Oh my god, 4.5 out of 5, so that did something. Oh my god. Oh, the only one is if it's not even in there. Okay, hold on. I swear, dude, I don't want to put a bunch of ifs. This is ridiculous. I feel like I'm putting like way too many ifs. Okay, I mean, I could put that literal sense, but... This is so many LFs. I'm putting so many LFs for this. Yeah, because it can't compare it if there's nothing there. What's the- I mean, I could put that literally, but I feel like I have to put the if. Oh, you know what? I had to do that one thing that he did on the other one. This lengthy freaking. If I had used this thing, it probably would have helped it because this checks to see if it has any of the letters in the alphabet. But I didn't think he was gonna make me write a whole extra code for that. Well, watch this is gonna work though, because that's the only other factor there is. Nope, I got 0 out of 5. Oh man, I just messed it up. Oh, string equals that, then false. Did it just make everything? No. String equals. What's wrong with that? Just do length 0. Okay. Yeah, you're right. That'd work too. Elif length of string equals 0. Return false. What am I doing? Why is that an invalid syntax? I don't understand. Invalid syntax. Wait, oh. I see what I did. That. Is that what I was looking for? Oh my god. I'm still messing up. That should have worked though. What? If string index out of range. But I got this. Or should I move this up? Just do length equals 0. Listen. Nearly did it. You haven't did it yet. You have did it. Case as another if. I have to put it before it, right? Here. I mean, like this. Just put that one first. No. I gotta put it separate or put the main if elif things inside the else. Something like that. Let's say if the string is equal to 0. If it doesn't equal, I mean, that works, right? If the 0 number. Um, yeah, it does equal 0. Okay. Well, then that should work. Yes. I'm gonna try it. Okay. Oh my god, it worked. I had to make it check that first. I probably could have worded this so much better. Like, and I think that was what I was. I think that's what he did with this last one. Is I mean, I didn't want to because I hope I didn't have to. I was kind of being lazy about it, but I should have created another function that checked to make sure that it had characters. That took like 40 minutes. Yeah, dude, hold on. Let's see how long it says. It says it should be completed in 18 minutes. I'm taking way longer than 18 minutes. And I don't even think this is the best way to do this. I mean, I was able to get there, but like, I feel like I should have organized this a bit better than this. Well, I probably also don't need this because I already have all the factors right here. But I was trying to make, but see, that's the other thing. I was trying to make it to where basically this is why I put the else return false at the end, because I was like, I thought this would make it work for anything, but if the character equaled the string, then return true, and then else if it's uh yeah, see, that's why I didn't even think I had to put if it's equal to 0 or oh yeah, oh never mind, this is my limit. Yeah, that's my limit. So I had to have this in here. But yeah, and then I mean I had this one to check it upwards. I had this one to check it downwards. I had this one if it equaled, and that's all I was thinking is I was like, if it's not equal, if it's well no, because it could still be greater or less than, it'll just bounce back and forth. Well no, because I have a limit. So once it runs out of the limit, then it hit false. That should have worked. And then if anything else, if it wasn't less than or equal to 0, but it wasn't greater, it wasn't less than, it wasn't equal, it should have just returned false. That should have worked for that problem. I would have thought we did our best for real. Yeah. That's why to do this is without doing the middle thing. Yeah, I would have made it easier, but I really feel like this should have worked instead of having to use this. Because that's why I put this here, was because I was like, if it's not equal, if my limit's not exhausted, if it's not greater, it's not less than, then it's false. Though I don't understand why that didn't work, but whatever. I'm kind of annoyed by that. Yeah, that don't make any sense to me. Whatever. But yeah, I was able to make a code that works for it. Hey, we both did. You did too, apparently. All right. Yeah, that 18 minutes, that was not 18 minutes.
Now that we have the ability to create functions, to define our own functions, we're going to be able to start solving some really neat problems, including some of the ones we've just looked at. But one of the...
I'm going to get some more water real quick. If you can reach them. If there is any, I don't know. Okay. Yeah, for real. Yeah, no, I was so locked in. It was, and then when I was checking the chat, you're like, "Hey, dude, I really need." There's there's plugins that some people have where the chat will like it'll ding or read or something like that. That's what I need. Because I literally I got the chat on like 2 screens, but I still suck at this. The cold striking us both. I was probably not as bad here. It's gonna be 70 degrees in 2 days, so yeah.
Michael,
Yeah.
I need help getting it.
Oh, why are you breathing so hard? Jesus.
Because I keep running.
Okay. Oh, the bathroom light's on. Oh, we live on the opposite side of the world. Yeah, for real. I know, it's crazy. It trips me out, dude, that like I mean, that stream usually like it's like I don't know how YouTube pushes stuff out. I mean, obviously there's a coding algorithm for it. But it does trip me out when like I get people on here from like places far crazy away, and I'm just like I don't even know how it reaches that crazy far away. I guess it's just the interest. If you have the interest for that thing, I guess that's I don't know. Look crazy. I don't know. I wish I could travel. Honestly, that'd be really cool to like go and travel and see places, different places and stuff. Cause I mean, we all got like similar interests worldwide, kind of, sort of, but like everybody like lives differently. Like the culture and everything's so different everywhere. I don't know. It's always interested me, but it costs a lot of money to travel. So,
The things that's going to happen is that we're going to be able to.
no, I don't know if I'll become a big YouTuber. I've been messing with this stuff for like 2 years now, so I'm kind of just. I'm like, we gotta try, Might as well give it a shot. See what happens. I don't know. I've been doing it for a minute though, so. But even if I don't, it's all good. But it'd be cool to get big. I'd definitely start traveling then. That'd be cool as hell.
Create lots of functions, and that means that we need to think about how to handle them. So far, we've assumed that all of our code is stored in one file. And that's cumbersome when I've got large collections of code, or especially when I've got a collection of code that's going to be used by different places or different people in different places, and I'd like to be able to access it directly. And so for that, we're going to introduce something you're going to use a lot. It's called a module. And basically, a module is a Python file that has something with the .py extension to it that's a collection of Python definitions of statements. Once I've got that module, I can use it, and I need to talk briefly about how do you use it. So for example, imagine I've created a little file called circle.py. It's a Python file called circle, and it's got in it a couple of simple functions for dealing with properties of circles. Compute the area, compute the circumference. I've also put a definition of pi inside of there. I've saved that file away, and now I want to use it. How might I use it? Well, I can import it. I can either import it into the shell itself, or I could import it, in fact, into some other file because I want to use it there. And so the usage here is if I invoke the command import circle, it goes and finds that file and reads all of the statements, including the definitions and assignments inside that file, into, in this case, the shell. Now, inside of the shell, I could redefine pi to be 3. That's okay because I'm walking inside the shell. I could print that out.
Oh, really? Well, shit, I don't know. I try to make the little thumbnails kind of interesting. Try to make them not too boring, but I try not to spend too much time on making them either. Because I have sat here before and like made thumbnails for like a couple of hours, you know what I mean? But
and in that case, it's going to print out 3. But then I could print out the value of pi that was defined in the module circle. And to do that, I use this notation here of circle with a dot followed by pi. It's telling me in the module circle, look up the value of pi. And that will print out what I defined there, 3.14159. And similarly, I could call the function defined in circle,
no.
and the dot that says...
Yeah, well, a lot of people say that I look like Mr. Beast.
Inside of the
So
circle.
that might be why. I don't know. Look, I say Mr. I mean, you probably know who Mr. Beast is, but especially when my hair is like. Apparently, I look like him. To some people, I don't know. Probably not right now with my hair. It's usually when I got like my hat on or something. Like, let's see. I don't know. I mean, I kind of got the little. I mean, I just got the facial hair. Like, that's all there really. I was like, I don't think my nose is way pointier than his nose. So I don't know. Well, that's what I get a lot. A lot of people say that, so I don't know.
Circle module, get the function called area, and call it on an argument 3, and it prints out something. And the same thing with circumference. So I can import things into my environment, whether again it's the shell, or as we'll see later on, inside of another environment, or sorry, inside of another file itself, because I want to use it there. If I don't want to refer to the functions and variables by their module, if I don't want to use that slightly clunky circle.py or circle.area, and I know that the names in that module don't collide with things I'm using directly, either inside the shell or inside of a new function, I can in fact do a slightly different version in which I say from a module, in this case circle, import everything. And the everything is done by simply giving it a star. That will bring all of the definitions, all of the assignments.
What?
Juice.
Juice?
Yes.
Goodness. Let's get your bottle. Come on. Let's get your bottle. Where's your bottle? Where's your bottle? Where's your bottle? It's not on the couch. Have you seen her bottle? Well,
into that environment. But now I simply refer to them by their name. I don't have to put that extra circle dot in front of them. This has the effect of creating bindings within the current scope for all of the objects defined within Circle. And the statements, as a consequence, within a module are executed only the first time a module is imported. If I want to redo something, I have to recall that actual invocation. But that gives me a nice way to start building modularity at a higher scale, by files as well as by functions. And that leads to the last piece we're going to deal with today, which is we need a way to save our work for later use. And we certainly have that if we do something inside of the text editor, but we also want to be able to do that inside of computations we're doing. Every operating system on a computer has its own way of handling files, and so Python handles this by providing an operating system independent way of accessing files called a file handle. And the way that is done is by using the special command open and giving it the name of a file and giving it a command. So in this particular case, open is going to open up a file handle, that is an access into a file with the name kids, and the W here says that it's open for writing. I'm going to be able to write into it. And I've bound that to a name so I can refer to it. Name handle is the handle that gets into that file. That allows me then to use it. So for example, I could write a little loop that says to the user, type in a name, and I'll write it into that file by, again, using name handle and the dot and then the write command. And this little extra character here is a string that just says do a carriage return or start a new line after the end of this write. I could do it as many times as I want. In this case, it was just going to be 2 times. But what I'm doing is I'm writing directly into a file, in this case called kids, things that I'm inputting on the terminal. You can imagine I'm also doing computations and writing them away. When I'm done, I close the file handle by invoking the method close. Again, with name handle, because that's the one I set up here, dot close, and the open close paren to say that it's actually an invoking.
I'm kind of confused. Hold on. Name handle equals open.
Of a function
That's
that closes
confusing
up
me.
the file. And finally, I can do the same thing where I want to read from a file by giving it the special string R. And in this case, I could read from that file and just print out a set of things, and when I'm done, again, close them off. So this gives you a little bit more power now, and it's part of that idea of modularity. I have function.
It's files. So you can, I don't know, I'm probably going to have to redo this because this confused the crap out of me. But I think it's basically, you can say, so you define a function, like how you do here. Yeah, I mean, you have like, you know, an individual function you defined, but he was saying that, I've seen this files thing first time in Python. Yeah. Yeah, I don't know. I've never seen this before, but I guess when you create one, instead of having to use it by putting this, you can import it. I don't understand why. I don't know. I don't really get it.
Now that we have the
I mean, I guess it's like a easier way to call it, maybe, or something. But I don't know.
ability
It's
to
confusing
create
me.
functions, to define our own functions, we're going to be able to start solving some really neat problems, including some of the ones we've just looked at. But one of the things that's going to happen is that we're going to be able to create lots of functions, and that means that we need to think about how to handle them. So far, we've assumed that all of our code is stored in one file. And that's cumbersome when I've got large collections of code, or especially when I've got a collection of code that's going to be used by different places or different people in different places, and I'd like to be able to access it directly. And so for that, we're going to introduce something you're going to use a lot. It's called a module. And basically a module is a Python file that has something with a .py extension to it that's a collection of Python definitions of statements. Once I've got that module, I can use it, and I need to talk briefly about how do you use it. So for example, imagine I've created a little file called circle.py. It's a Python file called circle. And it's got in it a couple of simple functions for dealing with properties of circles. Compute the area, compute the circumference. I've also put a definition of pi inside of there. I've saved that file away, and now I want to use it. How might I use it?
Wait, so it's saying like, okay, so you already created like the whole file, like one of these, like this whole file. Is that what it's talking about? What .py? That's what it's talking about, right? So you can call a file to another one. Yeah, .py. Okay, yeah. So that's the whole file. This is just one file of coding.
I've saved that file away, and now I want to use it. How might I use it? Well, I can import it. I can either import it into the shell itself, or I could import it, in fact, into some other file because I want to use it there. And so the usage here is if I invoke.
Yeah, that's what he's saying. Import said so. If you have, I don't know if I mean this is my first time hearing about all this, so I don't know. But like I guess if you have like this file, this entire file that you want to use, you just import the name right here into here. Can't we do that with, what's the difference between import and what he was talking about at the end? Well, something about what he was talking at the end was like, I don't know. I didn't know about this. This is new to me. So I guess you can import one file to another string of code. But, hello.
Hello.
What are you doing?
Hugging you.
Oh, okay.
Bye-bye.
Love you too.
Bye-bye.
Bye-bye. Are y'all having fun? Did y'all eat all the chips?
Yes.
Yeah. I got kids, so. Files, close, open. So, well, a file is, I mean, like, one of these, or like whenever these get saved, then it looks like this. And these are files. And they're, dots, it's the file name and then .py, because that's Python, that's the file type. And so, like, if I want to use one of these entire things and another code like this one, so, or whatever, I can put something like import game.py, which I don't know if it will, but imported but unused. So, and then maybe open? Something like that? I don't know. But yeah, that's one of the other files I have, yeah. You know all that? Oh, yeah, I don't know. So this is all new to me. I wasn't sure. Are you talking about the open and close? I don't know.
The command import circle. It goes and finds that file and reads all of the statements, including the definitions and assignments inside that file, into, in this case, the shell. Now, inside of the
yeah, that's what I was saying. I was figuring you knew about the import thing. I just couldn't tell. Well, what's the difference? I don't know. The only thing I know is this part. The other stuff confused me, so I still don't know what the open and close and stuff is. So import.
shell, I could redefine pi to be 3. That's okay because I'm walking inside the shell. I could print that out.
Oh, I don't remember.
In that case, it's going to print out 3.
Yeah, you might have brought up the import thing. If you did, I probably didn't remember because I didn't know what it did. But yeah, I don't know what open and close. I'm wondering if I don't know what the open and close does. I mean, I guess it's like you can open it for a period and then close it back if you need to close it back or something. Or not use it for the rest of the file? I don't know. Yeah, I don't know.
But then I could print out the value of pi that was defined in the module circle. And to do that, I use this notation here of circle with a dot followed by pi. It's telling me in the module circle, look up the value of pi. And that will print out what I defined there, 3.14159. And similarly, I could call the function defined in circle. Again, the dot that says inside of the circle module, get the function called area, and call it on an argument 3, and it prints out something. And the same thing with circumference. So I can import things into my environment, whether again it's the shell, or as we'll see later on, inside of another environment. Or it's
Okay, so you can import the whole thing, or you can import specific sections of another file by putting the period. Because what that other one looked like, where was it? Yeah, that's the, oh, where'd it go? Oh, dang it. Yeah. So you can import this function, or you can import this function from this file. That's a lot to remember.
out what I defined there, 3.14159. And similarly, I could call the
I don't
function
know.
defined in circle.
He's about to talk
being the
about
dot
it
that
here at the
says
end.
Inside of the circle module, get
I'm
the
just
function
trying to
called
grasp
area,
all
and
this.
call it on an argument 3, and it prints out something. And the same thing with circumference. So I can import things into my environment, whether again it's the shell, or as we'll see later on, inside of another environment, or sorry, inside of another file itself, because I want to use it there. If I don't want to refer to the functions and variables by their module, if I don't want to use that slightly clunky circle.py or circle.area, and I know that the names in that module don't collide with things I'm using directly, either inside the shell or inside of a new function, I can in fact do a slightly different version in which I say from a module, in this case circle, import everything. And the everything is done by simply giving it a star. That will bring all of the definitions, all of the assignments into.
Let's see. So, well, I did this one, but it says imported but not used. So, if I do it like that, does it from? No. Oh, maybe I can't find that one. It says imported but unused. I don't know. I mean, well, yeah, but if the star means all, then why don't you just put import circle? Wouldn't import circle be the same thing as putting from circle import? You know what I mean? There's a module called math. Type import math. Imported but unused. Yeah, if it's the same thing, I don't know why you would put this over just put import circle. Statements within a module are executed only the first time a module is imported. So maybe this is like a one-time import, like you use it once and then once it's used, then it doesn't do it again, maybe? Math random. It says imported but not used. I don't really know how to use it though. guess I'd rather try it here. Yeah, but I mean, I can only use them if I have them on my computer, right? Yeah, but I mean, it's not. That isn't doing anything though. Use A equals. Yeah, it keeps saying no module name math square root is not a package. God dang it. What'd I do? Just import math. Oh, that worked. Where does math come from? Is that one that's already in here somewhere? Huh. But you can use this for other files I create too, right? That's a predefined module. But wait, so are these modules like these whole things? Or like if I put something like palindrome. Okay, so if I put something like this, and then this is confusing. Undefined name. Imported but unused. Yeah, that. No module name palindrome. Oh, I guess. I don't know. You can import them when you make big projects. You do use those import things from your other files. Oh, okay. Alright.
To that environment. But now I simply refer to them by their name. I don't have to put that extra circle dot in front of them. This has the effect of creating bindings within the current scope for all of the objects defined within Circle. And the statements, as a consequence, within a module are executed only the first time a module is imported. If I want to redo something, I have to recall that actual invocation. But that gives me a nice way to start building modularity at a higher scale, by files as well as by functions. And that leads to the last piece we're going to deal with today, which is we need a way to save our work for later use. And we certainly have that if we do something inside of the text editor, but we also want to be able to do that inside of computations we're doing. Every operating system on a computer has its own way of handling files, and so Python handles this by providing an operating system independent way of accessing files called a file handle. And the way that is done is by using the special command open and giving it the name of a...
Aw, dang, you're killing me. Ugh. Yeah, seriously, it's hard when I got kids too. Ugh.
file and giving it a command. So in this particular case, open is going to open up a file handle, that is an access into a file with the name kids, and the W here says that it's opened for writing. I'm going to be able to write into it. And I've bound that to a name so I can refer to it. Name handle is the handle that gets into that file.
Oh, I see what
That allows me then to use it. So for example, I could write a little loop that says,
okay, so he defined a variable as opening. Oh. So this variable became opening for what? But that's not a file name, right? Using a file handle. This is kind of confusing. Creates a file named kids and returns file handle, which we can name and thus reference. The W indicates that the file is to opened for writing into.
name so
Oh
I
my
can
God,
refer
this is
to
so.
it. Name handle is the handle that gets into that file. That allows me then to use it. So for example, I could write a little loop that says to the user, type in a name, and I'll write it into that file by, again, using name handle and the dot and then the write command. And this little extra character here is a string that just says do a carriage return or start a new line after the end of this write. I could do it as many times as I want. In this case, it was just going to be 2 times. But what I'm doing is I'm writing directly into a file, in this case called kids, things that I'm inputting on the terminal. You could imagine I'm also doing computations and writing them away. When I'm done, I close the file handle by invoking the method close. Again, with name handle, because that's the one I set up here, dot close, and the open close paren to say that it's actually an invoking of a function that closes up the file.
Wait, so you created this variable to open the file kids and you put a W so you can write in it? Oh, man.
And finally, I can do the same thing where I want to read from a file by giving it the special string R. And in this case, I could read from that file and just print out a set of things, and when I'm done, again, close them off. So this gives you a little bit more power now, and it's part of that idea of modularity. I have functions giving me modularity. I can have collections of functions inside of files. I can create files as I'm interacting with them, and I can use all of those ideas to really control the complexity of the systems that I'm building.
Yeah, because the W, he's saying that the W just tells you that you can write in the file. And I'm putting an R tells you that you can read the file. But the file name's the first one.
Now that we have the ability to create functions, to define our own function.
That's a lot. It's gonna take me a while to completely remember that. Assume the 2 files below are in the same folder. You run inventory py. What happens? 2 files. Batteries py. File inventory py. A equals capital. 3A's equals capital. C equals capital. D equals capital. Assume the... Okay, so these are what the files are. Assume the 2 files below are in the same folder. You run inventory py. I guess it would only run inventory. And so it would print AA. I mean, if you only run inventory, why does this say? I don't know, dude. I'm like super confused right now. I mean, I'm assuming it's just saying like you have two files in a folder, but yeah. The second one, you run inventory PY, but you're running this one. All I don't understand. Why would it be the second one? Because this file would have to run. But you're not running this file. You're just running this file. So shouldn't it be this one? Oh. Oh shit, I didn't see that. Batteries.aa. Oh yeah, I didn't see that. Import batteries. Eh. Uh-oh. Well, I wonder if this one doesn't work because you can't print it if you don't import it first. There's an error. Maybe you have to, because you have to import it to use it. Well, oh, this is that function I was talking about earlier. This is the same thing as importing, but it's a one-time deal. Okay. Print AAA, C, and D. So I'm kind of confused. Well, because this is imported above this, so by the time you get to print, AA turns back into AA. But AAA would be capital, so it'd be this one. Oh, double check and make sure you're not a little behind on the video. Make sure it's like at the live part, because sometimes your video will take a second. It'll start being back by like a few seconds if it's not staying live. I got it on ultra low latency mode, so I mean it's gonna be keeping up as much as it can. I think it's got like a, I don't know, it's maybe like a second lag or something, but yeah, sometimes it can fall off behind on the actual live part, and it'll be like a second behind. You just gotta check it and make sure it's all the way forward. Pretty sure that's it. Yeah. Yeah, I mean, this ain't too complicating. It's kind of like, I mean, so you have files, and it's not complicating right now because I haven't put a bunch of stuff on top of it, but if you have two files and they're in the same folder, then you can basically call the whole file like as if you can call a function after you define a function, so, yeah. Recursion. Well, we already learned about recursion. Optional lab component to lecture. Play with an explorer. Oh. Okay. Define facts and if n equals 1, return 1 else. Fact is 5. Oh. That's gonna take away from it. Yeah. They should have showed me this earlier, honestly, when I was actually dealing with that stuff. Why is it going back to this? That's kind of weird. I don't know. I gotta put like neutral and stuff because it won't check it if I don't for some reason. This part's messed up. See, I get checks. Greater. A regular polygon has n number of sides. Each side has length s. The area of a regular polygon is, oh my god, okay, that's huge. The parameter of a polygon is length of the boundary of the polygon. Dude, are you... This seems hardcore. Write the function called polygon that takes two arguments n and s. This function should sum the area and square of the perimeter of the regular polygon. The function returns the sum rounded to 4 decimal places. This is an optional exercise, but great for extra practice. So it says I don't have to do this, but I mean, this is using the write a function called polysum. Oh, it wants me to create a function. This has nothing to do with what I was doing earlier. But it wants me to create a function that takes 2 arguments in and s. Should I do this? It says it's optional. First, import math. Can I import math on this? Because this is on the website. I don't know if it works like that. Do I have to? Yeah, but I mean, I don't have to import math on this one, right? You're talking about on this, or just like? But I mean, this is just wanting me to create a function. This ain't even. Wait. Which library should you be importing at the beginning of your code in order to call the tan function and to get a pi constant? Oh god. You need it for rounding off. Man. This is an optional one. Was I already supposed to know how to do that or something? So it does want me to import, call the tan. What is a tan function? The tangent of an angle using the math tan function from the built-in math module. Okay, this is. No, I don't know trigonometry. Trigonometry. I don't even know what that is. Trigonometry? What? Is a branch of mathematics that studies the relationship between angles and sides of triangles, particularly right angles, triangles. I just draw. What? Trigonometry is just about triangles? I mean, I know like a squared plus b squared equals c squared. It's taught in high school. Yeah, I mean, I know a squared plus b squared equals c squared, like that kind of stuff, but I don't know the ABC stuff. I mean, I don't know how hardcore this stuff goes, but I never use that. Tan, whatever. I don't know. Yeah, I don't even know. Pythagorean theorem. Yeah, I remember this one. Yeah, but I also haven't been in high school for, like 15 years, so there's that too. Ugh. Why are they teaching? Why do I gotta do so much math stuff? Is it always gotta be math stuff? I'm fine with doing math stuff, but I know how to like calculate like pressure and hydrostatic. You know what I mean? Like, I mean, I know a little bit about like quantum physics, but I mean, physics is cool, but I don't really know like a bunch of formulas and stuff. All right. Yeah, I don't know if I'm gonna know how to do this, but the area of a regular polygon is this. Oh, which function? Write a function that calls polysum that takes two arguments n and s. This function should sum the area and square of the parameter of the regular polygon. And so I mean, all I gotta do is put this in here, right? Like, uh, yeah. Yeah, I mean, but all this is it's just, I mean, I don't really need to know trigonometry for this. It's just telling me to use this equation. Oh, why does it do that when I click it? Another point. rounded to 4 decimal places. You gotta use math 10. Well, you gotta add NS. Well, I thought it's just S squared. Isn't that what that is? Because I thought it's just S squared, not the whole thing. It says add square of parameter. Oh, the area of a regular polygon. Area and square. Sum the area and square. Parameter is NS. Well, crap, I don't know. I haven't done this before. You wrote the area. So plus n square s square. I guess I could do it like that. About parameter. See, I don't know. This math stuff doesn't work for me. I don't remember none of this. This was a long time ago. The area of a regular polygon, write the function, takes 2 arguments in an S. This function should sum the area and square of the perimeter of the regular polygon. Well, oh, sum the area, so it's the area plus the square of the perimeter. The function returns the sum rounded to the 4 decimal places. I don't know, dude. Okay. I'd have to, like, I'm trying to learn coding, and this is like a bunch of extra math. Like, I don't feel like this is stuff that's probably why this is optional, honestly, but because then, like, in order to do this, I gotta go look up a bunch of stuff that I don't know. Yeah. Oh wait, don't use sum, use something. Oh. Sum is predefined. What is sum predefined is? There. Return the sum of a start value plus an iterable numbers. I don't know. Oh. It's like slightly off. Is it because the rounding? What does it say? Rounded to 4 decimal places. Rounding off is remaining. We gotta round off 2. The function returns the sum rounded to the, so I need to round sum. Read the whole question again, please. We're talking about this part. It says write a function called polysum that takes 2 arguments n and s. This function should sum the area and square of the perimeter of the regular polygon. The function returns the sum rounded to 4 decimal places. Well, we gotta round it to 4 decimal places. So I guess this is the correct equation, but we still gotta round it. That's the only part that I got rounded to 4 decimal places. But I mean, how do I round it to 4 decimal places? See, I figured it was something, some sort of extra one of them import things. Math round. Oh wow. See, yeah, I wouldn't have known that. I've never seen that before. He didn't show us that. How am I supposed to know it if he doesn't show me? Oh my god. Okay, so this round sum, and then I guess the 4 here is because the 4th decimal place. Oh no. Oh god. Hello? Oh. Yeah. Yeah, that sounds crazy. Yeah. You wonder if what? I mean, I don't know. I'd have to see it to believe it. Mm. Are you on your way home or something? Oh, so it, yeah, because you're dealing with money. You made what? Oh, hmm. Who? Uh, yeah. Oh, yeah. Mm. It's just the carbon copy. Yeah. Yep, we could hang out with them. Yeah, I don't know. They sound like they're really busy. They got two hybrid kids that are in school and they're both working full time jobs, so trying to survive. think. God dang. Yeah. I think I did everything I can do right now because this website's on the instructor or something. I don't know. And I got one problem set thing left to do, but that's like it, I guess. Unless, what is this? Important dates. More content coming soon. View course schedule. Okay. So there's two problem sets. Problem set 3 is not released yet. There's a midterm exam, but I have to be verified to take the midterm exam, and then there's problem sets, then final exam. Oh, finger exercises, not yet released. Those are the things I was doing. If it's not yet released, when does it come out? Why are there problems set so early? I don't know. That's what I'm... And this isn't even till February. Well, there's a midterm exam February 4th. I can't take it unless I pay for it, but... And then there's the rest of... Yeah, I guess I completed all the courses up until... What, finger exercise 5? When is that supposed to come out? I don't know. It says when they're due, like what time they're due, but it doesn't say. I mean, I guess between now and March. Set. See, set 1 and 2. God, it doesn't even say when these come out. It just says Wednesday, March 25th. And then. Not, okay, it says Wednesday, March 25th for the entire thing. So, and then it says that these ones after exercise 5, they're not released yet. Yeah. Yeah. Yeah, I can. Well, I can do go back to the boot.dev thing. There's some good YouTubers, that is true. Are you driving or something? You're driving to the tattoo shop? Oh. Oh. Huh? Yeah.
We have got to the point where literally anybody can build a fully working app without knowing how to code. This is Base 44.
What's up, everybody? In this video, I'm going to teach you everything you need to know to start coding with Python. I've also included 20 different hands-on projects to help you learn. You can find the entire list in the description of this video. Our final project will be a weather app that fetches real-time weather data from an API. Even if you've never coded anything in your life before, I'll walk you through the basics, the ABCs of programming. If that sounds good to you, then I encourage you to sit back, relax, and enjoy the show. This course doesn't cost you anything, but if you would like to help me out, you can help increase its reach by hitting the like button, leave a random comment down below, and subscribe if you'd like to be a fellow bro. Thank you, I appreciate it. I don't like boring introductions, so I say we just jump right in. There's two things we'll need to download. The first is a Python interpreter to convert our written code to machine code. We're going to head to python.org, go to Downloads, and download the latest version. We will open this executable, is an integer, an int. GPA is a float, is student, is a boolean. Using these typecast functions, we can convert from one data type to another. Here's how. So we will create a variable of length. We will accept some user input using the input function. What is our prompt? Let's say enter the length. Alright everybody, in this video we're going to create a game of Mad Libs. Not because we have to, but because I want to. It would be a good exercise for us, just so we're more comfortable with accepting user input. If you're not familiar with Mad Libs is a word game where you create a story by filling in the blanks with random
how you
words.
doing?
So we're going to create a story template. The story is going to be missing some components. We will fill in those components with random words that we type in. Here's a story that I've written myself. Print, use an F string. Today I went to a, insert a placeholder, zoo. For our placeholder, we'll insert an adjective. We'll insert a variable named adjective. Adjective 1. You're going to get an English lesson today too. An adjective is a description of something.
Well. Huh? We. I can't. No. So you're just going to the tattoo shop? You did your other thing. Did you get to wear your scarf? No. No. Yeah, I'd have to see him. That'd be a trip. He didn't even say anything. you too. You know, say hi.
Hi, Mama. I love you. What are you doing right now? Are you still in the car? Are you still in the car? Oh. Good. Hi. Okay. I'm gonna give you back to Michael. Because I do not remember anything you said. Olivia, no. I said.
0 hours.
Yvonne is my little Pookie Bear. We're in Arknex Enfield and we're checking Yvonne out. Respectfully, of course. I know. Yvonne is my little Pookie Bear. We're in Arknex Enfield and we're checking Yvonne out. Respectfully, of course. I know I said Pookie Bear.
Hey everybody,
Christ.
so today I gotta talk about iterables in Python. An iterable, it's a category. Any object or collection that can return its elements one at a time is considered an iterable. If an object or a collection is considered an iterable, then it can be iterated over in a loop. For example, let's create a list of numbers. Numbers equals a list. I'll add the numbers 1 through 5 to keep it simple. Lists are considered iterable. We can use them within a for loop. In the context of a for loop, we're going to be given each element one at a time. Not in Word. We would have to flip these statements around. If this... Hey, what's going on everybody? So in today's video I gotta explain list comprehensions in Python. A list comprehension is a concise way to create lists in Python. They're compact and easier to read than traditional loops. Basically, you have to follow this formula. For every value in something that's iterable, meaning you can loop through it, check some condition, then do this expression. So let me give you an example with using a traditional loop. Then you'll be able to see why a list comprehension is useful. We're going to create a list and double the numbers 1 through 10. Doubles equals an empty list. Using a traditional for loop, we will say for every value, let's say x, in range 1 through 11. Remember that in the range function, the second number is exclusive. This will give you the numbers 1 through 10. For the first iteration, x is going to be 1, then 2, 3, all the way up until 10. So we'll iterate 10 times. During each iteration, I'm going to take my list of doubles, use the built-in append method. We will append x during each iteration, that's going to be the value, times 2. So if I were to print my list of doubles, here's the result. We have the numbers 1 through 10 all doubled. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this is a lot to write. We can use a list comprehension to make this code more compact and easier to read. Here's how. We need a name for this list. Let's say doubles equals an empty list. Within our list, we'll follow this formula. We have an expression for value in iterable, and optionally, we can check a condition. We'll do this in exercises later on in this topic. We'll begin with for every value. Let's say X.
Oh, hey, I'm trying to learn the coding stuff. I mean, if you're not into it, it's all good. Yeah, I got the kids, and Breed's at the tattoo shop, so it's just me trying to learn coding right now. But yeah, I'm dealing with the kids at the same time, so that's why my stream's been kind of cutting on and off. But I was doing this class, but I kind of ran out of stuff to do on the class, so now I gotta, I don't know, find something else to do, I guess. I want to try this boot.dev thing one more time. Because this was kind of fun last time I did it. Because I was able to do Python, and I even did some SQL. You're bad at coding? I barely just started, so I'm on the same page. I mean, I can't be good at it. I barely started this a couple of days ago, so I figured, I mean, it's really interesting. I'm like digging it a lot, and I don't know. I'm hoping I can get somewhere with this. So I don't know. It's a lot to learn. It's a lot to grasp. So I don't know. I want to say maybe I could like try to. Good luck. Yeah, for real. Maybe I could try to do one of those things where they make something. I'm gonna go back to that one. He was making stuff. Maybe I can learn stuff. Because the only other thing, like, I'm starting to understand a lot of the functions and stuff. But, like, one of the things is, like, dude, there's a lot of, like, built-in functions that I don't even, like, one of the ones he just used, and I'm just like, where do you even find out all these functions?
Follow
Like,
this formula.
the built-in ones.
We have an expression for value in iterable, and optionally, we can check a condition. We'll do this in exercises later on in this topic. We'll begin with for every value, let's say X. In our iterable is going to be a range 1 through 10. Again, for the first iteration, X will be 1, then the second iteration, X will be 2, all the way up until 10. During each iteration, what would we like to do with X, our value? Let's take X, multiply it by 2, and return it. Then, if I was to print my list of doubles, we have the numbers 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. For every value in this...
You tried doing coding in a classroom and failed. Man, how'd you fail? If you're doing it in a class, then it's not... The point in a class is to teach you, so... I mean, did you fail, or did the class fail you? That's kind of like...
Iterable, do this. Multiply it by 2. This is a list comprehension. It's a concise way to create lists in Python. We'll go over a few exercises. So this time, we will triple each number. We'll create a list of triples equals, let's say this time for every y in range 1 through 10. So we have to write 11, take y, and multiply it by 3. Then we will print our list of triples. 3, 6, 9, 12, 15, 18, so on and so forth. Let's square each number. We'll create a list of squares for every...
This is the most replayed.
Security or IT degrees been on your mind, check out
Why does it say most replayed, but it doesn't say what the
Hello friends,
chapter
it's
is?
me again. Today I'm going to explain
It says most
modules.
replayed,
A
it's not
module is
match.
just a Python file containing code you want to include in your program. You use the import keyword to include a module. You can use built-in modules
that's the last
or
thing I
create
just
your own.
learned.
Sometimes it's useful.
It was all confusing. I couldn't focus. Too many numbers and words. Honestly, I totally get that. It's like, well, what makes it complicating is that even though there might be simple things like I understand what this does, I understand what this does, I understand what this does, but especially when it starts going in loops, when like one code triggers a repetitive pattern and loops back into itself, then it gets confusing, like because you could be like, you do one quick little short code, like one sentence, and it makes sense. But then when you take those codes and you start putting them all together to make a bigger thing, then it does get confusing. And it takes a lot of time of sitting there. And like that's why a lot of people say to draw it out too, because if you draw it out, you can like, instead of just sitting there staring at this code trying to figure it out, you can map it out and be like, okay, this code right here is going to do this, and then send it to a direction where you can write it out so you keep track of it. Because a lot of it's like you're trying to remember everything in your brain, and I mean, it's a lot to look at and it's a lot to remember and like think of all at the same time. So it gets super confusing. I mean, but I mean, I'm barely learning it, so it was like easy at first, and then it started getting really hard, and then yeah, but
To break up a large program into reusable separate files. For a list of all the modules found within the standard Python library, you can use the help function, pass in the word modules, and then we would need to print this.
What? Oh, that would have been good to know. What? Hold up. It says, oh my god. Let me shrink this down. Oh my god, I made that way too small. Okay, you're saying I can just put... Okay, hold on. Print. Help. Modules. Oh, wait. I didn't mean to return that. Okay. Hit that. Please wait a moment while I list. Oh my god. List of all available modules. Man, mine doesn't look like his. What? I guess so. The library pack is not. Please import. Enter any module name to get more help. Oh my god. Oh my god. Hey. I'll just stick to my art and building. Hey, that's cool, man. Art's awesome. This is just what I'm into. I mean, I'm just digging this. Hey, what's up, man? To a normal ID. Huh? Oh, no, this is a video. So I ran out of stuff on that class to do because they got to make more stuff, I guess. Or bring more stuff. So I started looking at other stuff. And then I started learning about modules. But I was like... And then I found out, I guess, these are all the modules. Like, that's a lot. That's like, how do you keep up with this? Like, oh, that is so much. Like, and then within each of these, isn't it like every single one of these does, like, can do a bunch of different things? Oh my god. This is a lot. Hey, look, there's GitHub. Yeah. Oh my god. Oh, there's math. Look, there's math. Oh my. See, this is a lot. What is it? What's wrong? Yeah, I don't know. This is crazy. Future, hello, fellow. Well, you don't need to memorize them. So how would you know when you need them? Enter any module name to get more help, or type module spam to search for modules whose name or your summary contain the string spam. What? So I mean, how do you know when you actually need one of these modules and something that you're working on? Like, cause this is a lot. What does it say? What is that gonna do? Nothing. Nothing. It says, oh, type modules. Oh my god. I don't know what it's saying. Or type module spam to search. What the heck? I don't know. You just sometimes Google if something you want to do is already in some module. Yeah, I guess that's the only way you would know how to do that. You'd have to Google it. Because I couldn't imagine anybody actually remembering what all of these things do. What is asteroid? Was it print help asteroid? Asteroid is not defined. Oh, crap. Ah, what? Package contents. So what? Asteroid manager, bases, brain builder. Manager, rebuilder. The aim of this module is to provide a common base representation of Python source code for projects such as PyChecker. Well, actually, the development of this library is essentially governed by I don't know. That's a trip, dude. This is. Whew.
Here are many of the different modules available to you. A few you may recognize would be math, string, time. One of my favorite names of a module is the pickle module. Unfortunately, it doesn't have anything to do with pickles. It's used for serialization. To list all of the different variables and functions found within a module, you can place that name of the module within the help function. For example, with the math module, here are a few different variables we would have access to, and a few different functions. To include a module, we would type import the name of the module. For example, math. I now have access to everything found within the math.
It looks like something really niche. Yeah, dude, I was like, dude, this is the Asteroid one. All I'm thinking is Asteroid the game, you know, like the old school Asteroid game. And I don't even know. It's like, I'm reading it, but I still don't. Yeah, it's definitely for something very in particular, but I guess you gotta, I don't know.
Module, including those variables and functions. To access those variables and functions, I would normally type the name of the module dot the name of the variable or function, such as pi. Then let's print this. Pi from the math module is 3.14 and some change.
Oh.
Another way to import is to type import the name of the module as, you can give your module a nickname, an alias, whatever you think of, such as M. M short for math. We would no longer refer to this module as math. We would refer to it as our alias, M. Using an alias would reduce some of the typing you have to use if you have a very long module name. Another way to import is to use from the name of the module, import something specific. Pi, for instance. You would no longer need the module name. From math, import pi. Pi would be included within our namespace. However, I tend to not use from import as much, just because it's possible there could be name conflicts. Here's an example. Let's say from math, import e. E is an exponential constant. E is 2.71. What if I was to create a program where we have 4 variables named A, B, C, D? A equals 1, B equals 2, C equals 3, D equals 4. Then I'm going to print E from the math module to the power of A. That would give me 2.71. Then let's do this with B, C, and D. E to the power of B, E to the power of C, E to the power of D. Here are the results. Let's say we have a different variable, E. E will be 5. Then I will print E to the power of E. We have imported E from the math module. When we have declared all of these variables, technically what we've done is we have created another version of E. We will end up using the second version rather than the version that we have imported from the math module. All my results are now different, and it's possible you may not realize it. I like to be more explicit. I'm going to import math. If I'm using a variable or function from a module, I much prefer to prefix that variable name or function with the name of the module in which it's from. Math.e to the power of A, to the power of B, to the power of C, to the power of D, math.e to the power of our variable E. And these results are to be expected. Now, to create a module, what we're going to do is right-click on our project folder, go to New, Python file, think of a module name, maybe example, then click Python file. We now have 2 tabs, main and example. Declare whatever you would like.
No, you can't have that. No. No. Okay, you can take off your shoes, but you can't have that. No. No, that's not yours. No. Stop. Olivia. Stop. Okay. You just had ravioli. You don't pin. What? Oh my god. All right.
Within this module, let's create our own variable pi. Pi equals 3.14159, then a few functions. Let's create a function to square an argument that's passed in. Define square. We will accept an argument which we will name x, then return x to the power of 2. Let's define a cube function. We will accept one argument, then return x to the power of 3. Maybe a circumference function. Define circumference. We will accept a radius, then return 2 times pi times radius. Then an area function to calculate the area of a circle.
You don't have to do so many,
We will
man. I
accept
thought
a
I'm
radius
kidding
as
what
an
you're
argument.
saying, dude.
Then
Like,
return pi times radius.
he's just showing off
to
at
the
this
power
point.
of 2. All right, here is our example module. Within our main Python program, let's import the name of our module, which we
Example.
named example. We now have access to everything within this module. I'm going to declare a variable result and set it to the name of my module dot pi. Then I will print the result, which is 3.14159.
That's cool. I
Let's
like it.
utilize the square function. Result equals example dot square. Let's square 3, which is 9. Let's use the cube function. That would be 27. Circumference. That would give me 18.8. Then area. That would be 28.2. That's how to create your own module. It can be useful at times to separate your program into individual files. Alright everybody, in conclusion, a module is just a file containing code you want to include in your program. You use import to include a module. You can use built-in modules or create your own. If you do need a list of the modules available to you, again, you can use the help function, then pass in the word modules. And well everybody, that's how to get started with modules in Python.
I like that.
You.
That was nice.
Just you.
I didn't know all that.
Building your app. On base 44. Describe it. And it's real. One thought.
Hey friends, it's me again. Today I'm going to explain both variable scope and scope resolution. Variable scope is where a variable is both visible and accessible. With scope resolution, when we're using a variable, there is a certain order known as the LEGB rule in which we locate that variable. Local, enclosed, global, built-in. We'll get to this momentarily. Let's begin with variable scope. I have two functions, function 1, function 2. Within function 1, a equals 1, then we print a. Within function 2, b equals 2, then we print b. If I were to invoke these functions, let's invoke function 1, then function 2. We would print 1, then 2. Variables declared within a function have a local scope. Variable a is local to function 1, variable b is local to function 2. Within function 1, if I were to print b, and function 2, if I were to print a, we would run into a name error. Name b is not defined. And the same thing would apply with a. Functions can't see inside of other functions. Imagine that we're function 1. This is our house. We can see everything that's going on inside of our house. But function 2 is our neighbor's house. We can't see what's going on
I
inside
feel like I
our
already
neighbor's
know all
house.
this stuff. I like the
We
way
have
he's
no idea
explaining
what
stuff,
E
though. This is really
With
cool.
function 2 has no idea what A is. That's where variable scope comes in. It's where a variable is visible and accessible. Functions can't see inside of other functions, but they can see inside of their own function. That's why we sometimes pass arguments to functions so that our functions are aware of them. Using this concept, we could create different versions of the same variable. Let's rename A to be X and B to be X as well. Then I will print X. We have two different versions of X. A local version of X found within function 1 and a local version of X found within function 2. Whenever we utilize a variable, we will first look to see if there's any local instance of that variable. If there isn't,
Yeah, well, I didn't completely finish the MIT stuff, but it's a they're not the rest of the class. I guess isn't getting released until a certain time limit or something. Is basically where it's at. It's like, here, let me go. Yeah. View course schedule, but it's not saying like, so it says when some of this stuff's coming out, like the problem sets, but well, this problem sets. I mean, this one ain't even. I already did this one. This one's due February 12th, and then, but see, like like this is the next I'm supposed to do, but it's not released yet, and it says it's due 6:30, but I don't know what day. I don't know. This is, but I guess this is as far as I got so far. And so I'm not really sure why it stopped here, but I don't know. It's kind of weird. I mean, I could, what, I don't think I did these yet. What, problem set 2? I guess I didn't do these. Oh yeah, this was the math stuff. This looks like so. I just want to learn coding stuff, and this doesn't look like just coding stuff, but I could try to figure this one out. The following variables contain values as described below. Balance, outstanding balance, critical. For each month, calculate statements on the monthly payment and remaining balance. Monthly payment or remaining balance at the end of the 12 months. Print out a statement of the remaining balance. Be sure to print out no more than 2 decimal digits of accuracy. So print remaining balance. So I gotta do like a round thing here, I guess. So your program only prints out one thing. The remaining balance at the end of the format. A summary of the required math is found below. Monthly interest rate, annual interest rates, 12. Minimum monthly payment, minimum monthly payment rate times previous balance. Monthly unpaid. We provide sample test cases below. We suggest you develop your code on your own machine and make sure your code passes the sample test cases before you paste it into the box below. Test cases to test your code with. Be sure to test these on your own machine and that you get the same output before running the code on this web page. No. What? So I gotta run this on mine to make sure it's actually. Wait. Use the round function at the end of your code. And 2 decimal digits of accuracy. How do you use round? It's like, believe. The way we use the round function is a equals round a number to a given precision in decimal digits. Maybe. Okay, that's all I gotta do. Okay, I got it. Alright. Test case. result your code should be generated below. To make sure you are doing calculations correctly, this is the remaining balance you should be getting at each month for this example. Results your code should get generated below. Depending on where you round in this problem, your answer may be off by a few cents in either direction. Do not worry if your solution is within 5 cents of the correct answer. Be sure to test these on your own machine and you get the same output before. Okay. Oh, were you talking about the round thing? Looking for algorithms course could still be beneficial. Yeah, because I mean, this is like, I mean, all I'm gonna be using is stuff like I already know, so I don't really know if I should put the time into like messing with this right now. Because like I could probably figure this out, but like, I mean, that was one of the reasons I haven't messed with this though, is because I'm wondering if I should be like trying to find something that maybe I don't know about, but I don't really know where I should be like looking. Or are you saying looking for an algorithm course? I mean, I guess like at this point, that's kind of like my biggest thing is I don't really know what I should do. I mean, I still have this dude, the boot.dev stuff, which it's got to learn Python thing too, and I made it a little ways in here, but I can't use this because it's free to watch and stuff, but I mean, I got to use my own coding thing, and then I don't know if I did it right because all I can do is run it in mine, and I can't see what so that's the only reason I haven't been doing this one, because you can still learn everything, but you can't tell if you're doing everything right unless you pay for it, and I don't know. It's not cheap, but it's not free. It's just hard to determine like what I should do, especially when I was onto something that was like taking me through stuff, and then it just kind of stopped, and I'm just like, I don't like the way it just kind of stopped. It's like, yeah. I ain't doing that sandbox stuff. But I guess I have to do this. That's a lot to read though. But this, I don't know. I don't know if I should be learning this. I don't know if I should be trying to learn something else or not. Monthly interest rate. So these are the following variables that contain values as described below. The outstanding balance on the credit card. Oh, monthly payment rate. Oh yeah, that was that other one I did. Wait, does it want me to? Balance. Okay, it wants me to print. Okay, if the balance is 42, the annual interest is 2, and the monthly payment is 4. Then there. Maybe there's a algorithm course on MT. I don't know. Computer science for Python programming, introduction to Python programming. I guess that's the one that it did. That I started on Python data science. Python basics for data science. Computer. Oh, this is introductory level. That's the one I was doing. Introduction to Python programming. That's another one. Georgia Institute. Oh, what happened? There's algorithms and data structures. I don't know if that's. But do you want more juice?
Yeah.
Oh my goodness. Algorithm and data structures often.
Lick. By figure.
Capstone.
Ew. Nine.
I don't really know where I should be trying to start on with this.
Ew.
This truck's
Now mine. Oh.
I mean, I could do this. I don't know what capstone is. What is this? What about this one? Self-paced. Mm, I don't know. Is there like a website that you know that's better for that? What is this? This says intermediate. I don't know. Hmm. Oh, I guess this one ain't free. Hmm. Hmm. No, some of these are free, not all of them are. I think MIT is the only free one. Hmm. Computational thinking using Python. What is that? No, I can't already do that one. I do the MIT stuff because the MIT stuff's the stuff that's free. Man, I don't know. Screw it. I'm gonna see if I can figure this stuff out. I might as well because I'm just like scrolling around. I don't know what to do. Alright, monthly payment rate, annual interest rate, balance, 42, and I needed to show the monthly balance and the remaining balance at the end of the year. So, I'm not sure about good online courses I would recommend if I knew some. Yeah, I don't know. I just heard about the MIT stuff, so I started doing that because it's free. And then I was doing the boot.dev, but to be interactive with it, to know if you're answering questions correct, then you have to pay. The MIT, I mean, it still is interactive, but if you want a certificate, then you have to pay. But MIT is like a real college, so I mean, they kind of got more to, I guess, talk about or whatever, or to use. Monthly balance is, I mean, you're gonna have to enter a balance. Okay. interest rates and monthly payment rate. Come on. Okay, so I need a reoccurring. So I gotta do a loop for a monthly payment. So it's gonna be let's balance. Balance equals takeaway. Monthly payment rate plus what times annual interest rate. Times annual interest rate. Am I doing that right? I wonder if it'll let me do an F string. Yeah, I did see it. Yeah, I saw you hit 500. I was like, that's awesome, dude. I'm cranking in the numbers. Let's see. Balance. was this? You've been playing Rocket League or what? Playing Rocket League a lot? I don't know if you're still there. I'm probably checked into. I'm doing all this boring stuff. Okay. What is this? Ooh, I messed up. Reloaded modules. What? Let's see. Well, month is greater than. Oh my god. Did I really? A month equals 0. While month is less than 13. Month plus equals 1. Balance 42. Take away monthly payments. Payment rate. What? Minimum monthly payment rate as a decimal. Annual interest rate as a decimal. What? Was that? So the monthly payment rate's 4%, and the annual interest rate's 20%. Remaining balance 31.38. I mean, this should print something though. I ain't printing nothing. Oh, I didn't call the function. Oh my god. Crap, what'd I do? I messed up. There it goes. Oh, it also did 13. Nope. Oh. Okay, got that part. Now I gotta start doing the math right. Okay, so the balance is $2. I found an MIT course on algorithms, though it may be too mathy. It's also not on EDX, but on the MIT website, so the problems are in PDFs. It's called MIT. Are they like this or something? This one's super mathy. It's, I mean, this is like their problem things. I don't know if this is gonna be like this, but I'm down to look it up. Introduction to algorithms. How he uses algorithms to create origami figures. Oh, Lex, yeah. Man, I can download this. Is this the one you're talking about? Oh, what is it? Oh, here it is.
The following content is provided under a Creative Commons.
Oh, I can see it. The videos are super low quality. Lectures, problem solving. What are these videos? Exams. This. It's the 2011 one. Oh yeah, I got 2011. The previous was 2020. How do you get the new one? Topics. Oh, is this the new one? It just looks weird because it's picture, but oh yeah, this is the 2021. 6.0, yeah. Oh, so this is the new one. It just looks weird because he looks like he's holding a snake. Like, I was like, this doesn't look like it has to do with algorithms. I mean, it said introduction to algorithms, but like I guess that's him doing. He's using algorithms to create complex origami things, and I thought it was just like some dude holding a snake. I was like, what the heck? Well, should I download that one? Yeah. Yeah, that's the new one, 6.006. No, it's already completed. Okay. I got it in a zip folder. Let's see. Okay. open the home page, click the index file to find the static resources. Oh, these are the PDFs. And then, where'd that other thing go? Oh, what is this? Why does it look so weird? What? What the heck? What was the point in downloading this? This ain't... What is this? I mean, the videos are on here. Oh, that's the wrong one. That's the other one. I mean, I can see the videos here. But... to open home. I guess this just has... What are these? Oh. Can't open all that in one. Man, that's a lot of reading. I'll click on the lecture videos. Huh? Yeah, sorry, I was messing around too much. I got ADD. I get distracted.
Good morning, everybody. My name is Jason Koo. I'm going to be teaching this class in Introduction to Algorithms with two other instructors here, faculty in the department, Eric Demain and Justin Solomon. They're excellent people, and so they will be working on teaching this class with me. I will be teaching the first lecture, and we'll have each of them teach one of the next two lectures, and then we'll go from there. Yeah, so this is Intro to Algorithms. Okay, so we're going to start talking about this course content now. What is this course about? It's about algorithms, right? Introduction to Algorithms. Really what the course is about is teaching you to solve computational problems. But it's more than that. It's not just about teaching you to solve computational problems. So solve, goal. 1, solve computational problems. But it's more than that. It's also about communicating those solutions to others and being able to communicate that your way of solving the problem is correct and efficient. Okay? So it's about two more things. Prove correctness, argue efficiency, and in general, it's about communication. I can't spell, by the way. Communication of these ideas. And you'll find that over the course of this class, you'll be doing a lot more writing than you do in a lot of your other courses. It really should maybe be a CI kind of class, because you'll be doing a lot more writing than you will be coding, for sure. So it's really, of course, solving the computational problem is important, but really the thing that you're getting out of this class and other theory classes that you're not getting in other classes in this.
Hello? Hey. Oh, watching a video about algorithms. It's like a MIT class. Alright. Yeah. Yeah. Mm. 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 Love you too. Alright. Bye. What? No, I didn't. That's why I said what. You're just like making noises. Love you. Alright. Bye. Okay.
Department is that we really concentrate on being able to prove that the things you're doing are correct and better than other things, and being able to communicate those ideas to others and not just to a computer, right? To other people, convince them that it's correct. Okay, so that's what this class is about. So what do I mean when I say solve a computational problem? What is a problem? What is an algorithm, right? I know people make fun of me because I start with this question, but I mean, anyone want to answer that question? No? What's a problem computationally? No? Okay, so it's not such a stupid question. Yeah?
Ain't no one saying nothing.
Something you want to compute. Okay, yes, that's true, right? But kind of a little bit more abstractly, what I'm going to think of a computational problem being, and this is where kind of your prerequisite in discrete mathematics should come in, right? It's a problem is kind of, you've got a set of inputs. Okay, maybe I have 1, 2, 3, 4, 5 possible inputs I could have to my algorithm. Okay, then I have a space of outputs. Okay, outputs, and maybe, I don't know, maybe I have more of them than I do inputs, but these are the possible outputs to my, my problem. And what a problem is a binary relation between these inputs and outputs. Essentially, for each input, I specify which of these outputs is correct, right? It doesn't necessarily have to be one, right? If I say, give me the index in an array containing the value 5, there could be multiple 5s in that array, and so any of those indices would be correct. So maybe this guy maps to that output, and maybe this guy maps to, I don't know, 2 or 3 outputs, right? This input goes to 1, 2, I don't know. There's some kind of mapping here. These edges represent a binary relation. It's kind of a graph, a bipartite graph between these inputs and outputs. And these are specifying which of these outputs are correct for these inputs. All right? That's really the formal definition of what a problem is. Now, generally, if I have a problem, a computational problem, I'm not going to specify the problem to you by saying, okay, for input 1, the correct answer is 0. And for input 2, the correct answer is 3, and so on and so forth. That would take forever, right? Usually what we do when defining a problem is specify some kind of predicate saying that, oh, we can check. If I give you an input and an output, I can check whether that output is correct or not. That's usually how we define a problem. If I am checking for whether this index contains a 5, I can just go to that array, look at index 5, and say, or the index you gave me, and see if it equals 5, right? So usually we're putting it in terms of predicates because in general, we don't really want to talk about small instances of problems. So let's say I had the problem of, among the students in this classroom, do any pair of you have the same birthday? Okay? All right, well, probably if there's more than 365 of you, the answer is yes. Right? Right? That by what? Pigeonhole principle, right? 2 of you must have the same birthday, right? But, so let's generalize it a little bit. Say that, I don't know, I need a bigger space of birthdays for this question to be interesting. Maybe I tack on the year. Maybe I tack on the hour that you were born. And that's a bigger space of inputs, and I wouldn't necessarily expect that 2 of you would be born in the same year, on the same day, in the same hour, right? That would be a little less likely. In fact, as long as that space is larger than something like the square of the number of you, right, then I'm less likely than even to have a pair of you. That's a kind of a birthday problem you may have seen in 042 potentially, right? But in general, I'm not going to mess with probability so much here. I want a deterministic algorithm, right? A way of checking whether 2 of you have the same birth time, let's say. Okay, so in general, in this class, we're not going to concentrate on inputs such as, is there a pair of you in this class that have the same birthday? That's kind of boring, right? I could just say, well, I could do a lot of different things, but what we do in this class, this is for a fixed classroom of you. I want to make algorithms that are general to any classroom, right? To go to your recitation, I want an algorithm that will apply to your recitation. I want an algorithm that not only applies to this classroom, but also the machine learning class before you, right? I want an algorithm that can change it can accept an arbitrarily sized input, right? Here we have a class of maybe 300, 400 students, right? But I want my algorithm to work for 1 billion students, right? Like maybe I'm trying to check if there's a match of something in the Facebook database or something like that, right? Okay, so in general, we are looking for general problems that have arbitrarily sized inputs, right? So these inputs could grow very large, but we want a kind of a fixed size algorithm to solve those problems, okay? So what is an algorithm then? What am I? No. I really can't spell. Told you. Okay. I didn't lie to you. So an algorithm is a little different than a problem. A problem specification, I can state to you what this graph, or I can tell you what this graph looks like. An algorithm is really, I don't know what the outputs are. I don't know what these edges are. But I want a fixed size kind of machine or procedure that if I give it an input, it will generate an output. And if it generates an output, it better be one of these correct outputs, right? So if I have an algorithm that takes in this input, I really want it to output this output, or else it's not a correct algorithm. Similarly, for this one, it could output any of these 3 outputs, but if it outputs this guy for this input, that would not be a correct algorithm, right? And so generally what we want is an algorithm is a function. It takes inputs to outputs, right? An algorithm is some kind of function, right, that takes these inputs, maps it to a single output, and that output better be correct based on our problem, okay? So that's what our algorithm is. It solves the problem if it returns a correct output for every problem input that is in our domain, okay? And the example for, does anyone have a possible algorithm for checking whether any 2 of you have the same birth time as specified before? I'm going to let someone else have a try. Sure. Great, so what your colleague has said is a great algorithm. Well, essentially what it's going to do is I'm going to put you guys in some order, okay? I'm going to give each of you a number, 1 through however many number of students there are in this class, and I'm going to interview you one by one, right? I'm going to say, what's your birthday? And then I'm going to write it down, right? I'm going to put it in some kind of record, okay? And then as I keep interviewing you, I'm going to find out your birthday. I'm going to check the record. I'm going to look through all the birthdays in the record. If I find a match, right, then I return, yay, I found a pair, and I can stop. Otherwise, if I get through the record list, I don't find a match, I just stick you at the end of the record, right? I add you to the record, and then I move on to the next person. I keep doing this. Okay, so that's a proposed algorithm for this birthday problem. For birthday problem, what's the algorithm here? Maintain a record. Interview students in some order. And what does interviewing a student mean? It means 2 things. It means check if birthday in record. And if it is, return a pair. So return pair. Otherwise, add new student to record. And then at the very end, if I go through everybody and I haven't found a match yet, I'm going to return that there is none. Right. Okay, so that's a statement of an algorithm. That's kind of the level of description that we'll be looking for you in the theory parts of this theory questions that we ask you on your problem sets, right? It's a verbal description in words that, it's maybe not enough for a computer to know what to do, but if you said this algorithm to any of your friends in this class, right, they would at least understand what it is that you're doing. Yeah? Pure function does an algorithm have to be a pure function in the mathematical sense, as in it needs to map to a single output?
As in it can't modify some external state, it can't take in a state, and it can't do IO.
So we're talking about kind of a functional programming definition of a function, right? This is, I am talking about the mathematical, I have a binary relation, and this thing has an output for every input, and there is exactly one output to every input. That's the mathematical definition of function that I'm using for when I'm defining an algorithm. Yeah? Yeah, an algorithm is a procedure that somehow I can do whatever I want, but I have to take one of these inputs, and I have to produce an output, and at the end, it better be correct. Right? So it's just a procedure. You can think of it as like a recipe. You can think of it as, it's just some kind of procedure, right? It's a sequence of things that you should do, and then at the end, you will return an output. Okay, so here's a possible algorithm for solving this birthday problem. Okay? Now, I have given you what I argue to you, or I'm asserting to you, is a solution to this birthday problem. And maybe you guys agree with me, and maybe some of you don't, right? So how do I convince you that this is correct, right? Well, if I had, if I was just running this algorithm on, say, the 4 students in the front row here, right? I could argue it pretty well to you. I could go through every, I could assign these 4 people birthdays in various combinations of either none of them have the same birthday, some 2 of them have the same birthday. I could try all possibilities, and I could go through lots of different possibilities, and I could just check that this algorithm returns the right answer in all such cases, right? But when I have, I don't know, 300 of you, that's going to be a little bit more difficult to argue. And so if I want to argue something is correct in mathematics, I want to prove something to you for some large value, what kind of technique do I use to prove such things? Yeah, induction, right? And in general, what we do in this class, what we do is, as a computer scientist, is we write a constant size piece of code, right, that can take on any arbitrarily large size input, right? If the input can be arbitrarily large, but our code is small, then that code needs to loop or recurse or repeat some of these lines of code in order to just read that output, right? And so that's another way you can arrive at this conclusion, that we're going to probably need to use recursion, induction, and that's part of the reason why we ask you to take a course on proofs and inductive reasoning and discrete mathematics before this class. Okay, so how do we prove that this thing is correct? We got to use induction. So how can we set up this induction? What do I need for an inductive proof? Sure. Base case, we need a base case. We need some kind of a predicate, yeah, but we need some kind of statement of a hypothesis of something that should be maintained, right? And then we need to have an inductive step, which basically says I take a small value of this thing, I use the inductive hypothesis, and I argue it for a larger value of my well-ordered set that I'm inducting over, right? Okay, so for this algorithm, if we're going to try to prove correctness, what I'm going to do is I'm going to, what do I want to prove for this thing? That at the end of interviewing all of you, that my algorithm has either it has returned with a pair that match, or if we're in a case where there wasn't a pair somewhere in my set, that it returned none, right? That would be correct, right? So how can I generalize that concept to make it something I can induct on, right? What I'm going to do is I'm going to say, let's say after I've interviewed the first K students, right? If there was a match in those first K students, I want to be sure that I've returned a pair, right? Because if after I interview all of you, I've maintained that property, then I'll be sure at the end of the process I will have returned a pair if one exists. So here's going to be my inductive hypothesis. Okay, if first K students contain a match, algorithm returns a match before interviewing, say, student K plus 1. Okay, so that's going to be my inductive hypothesis. Now, if there's n students in this class, right, and at the end of my thing, I'm trying to interview student n plus 1. Oh, student n plus 1's not there. If I have maintained this, then if I replace k with n, then I will have returned a match before interviewing the last student, or when I have no more students left. And then this algorithm returns none, as it should, right? Okay, so this inductive hypothesis sets up a nice variable to induct on, right? This k I can have increasing up to n, starting at some base case. So what's my base case here? My base case is The easiest thing I can do, sure. 2, that's an easy thing I could do. I could check those possibilities, but there's an even easier base case, yeah. There's an even easier base case than 1. 0, right? After interviewing 0 students, I haven't done any work, right? Certainly the first 0 can't have a match, right? And so this predicate, this inductive hypothesis, is true just because this initial predicate is false, right? So I can say, you know, base case 0, check. Definitely this predicate holds for that. Okay. Now we get to go for the meat of this thing, right? Assume the inductive hypothesis true for k equals, say, some k prime. Okay, and we're considering k prime plus 1, right? Then we have 2 cases. One of the nice things about induction is that it isolates our problem to not consider everything all at once, but break it down into a smaller interface so I can do less work at each step, right? So there are 2 cases. Either the first k already had a match, right? In which case, by our inductive hypothesis, we've already returned a correct answer, right? The other case is it doesn't have a match, and we interview the k plus 1th student, the k prime plus 1th student. If there is a match in the first k prime plus 1 students, then it will include k prime plus 1, the student k prime plus 1, because you know, otherwise there would have been a match in the things before it, right? So there are 2 cases. If k contains match k prime, if first k contains match, already returned, turned by induction, right? Else, if k prime plus 1 students contains match, the algorithm checks all of the possibilities. K prime checks k against all students, essentially by brute force. It's a case analysis. I check all of the possibilities, right? This check if birthday is in record. I haven't told you how to do that yet, but if I'm able to do that, I'm going to check if it's in the record. If it's in the record, then there will be a match and I can return it. Otherwise, I have reestablished the inductive hypothesis for the k prime plus 1 students. Does that make sense? Yes? Yeah. Okay, so that's how we prove correctness. This is a little bit more formal than we would ask you to do in this class all the time, but it's definitely sufficient, you know, for the levels of arguments that we will ask you to do. The bar that we're usually trying to set is if you communicated to someone else taking this class what your algorithm was, they would be able to code it up and tell a stupid computer how to do that thing. Okay?
I gotta pee real quick. I'm kind of thinking about switching this out with the other one.
so any questions on induction? You're going to be using it throughout this class, and so if you're unfamiliar with this line of argument, then you should go review some of that. That would be good. Okay, so that's correctness, being able to communicate that the problem, the algorithm we stated was correct. Now we want to argue that it's efficient, right? What does efficiency mean? Efficiency just means not only how fast does this algorithm run, but how fast does it compare to other possible ways of approaching this problem, right? So how could we measure how fast an algorithm runs? This is kind of a silly question, yeah? Yeah, just record the time it takes for a computer to do this thing, right? Now, there's a problem with just coding up an algorithm, telling a computer what to do, and timing how long it takes. Why? Yeah. It would depend on the size of your data set. Okay, we expect that, but there's a bigger problem there. Yeah? It depends on the strength of your computer, right? So I would expect that, if I had a watch calculator and I programmed it to do something, right? That might take a lot longer to solve a problem than if I asked, IBM's research computer, right, to solve the same problem using the same algorithm, even with the same code, right? Because its underlying operations are much faster, right? How it runs is much faster. So I don't want to count how long it would take on a real machine. I kind of want to abstract the time it takes the machine to do stuff out of the picture. What I kind of want to say is, let's assume that each kind of fundamental operation that the computer can do takes some fixed amount of time, okay? How many of those kinds of fixed operations does the algorithm need to perform to be able to solve this problem, right? So here we don't measure time. Instead, count kind of fundamental operations, okay? We'll get to what some of those fundamental operations are in a second, but the idea is we want a measure of how well an algorithm performs, not necessarily an implementation of that algorithm, right? Kind of an abstract notion of how well this algorithm does. And so what we're going to use to measure time or efficiency, right, is something called asymptotic analysis. Anyone here understand what asymptotic analysis is? Probably, since it's in both of your prerequisites, I think. But we will go through a formal definition of asymptotic notation in recitation tomorrow, and you'll get a lot of practice in comparing functions using an asymptotic analysis. But just to give you an idea, right? The idea here is we don't measure time, we instead measure ops, and like your colleague over here was saying before, we expect performance. I'm going to use performance instead of time here. We expect that to depend on size of our input, right? If we're trying to run an algorithm to find a birthday in this section, we expect the algorithm to run in a shorter amount of time than if I were to run the algorithm on all of you, right? So we expect it to perform differently depending on the size of the input, and how differently is how we measure performance relative to that input. Usually we use n as a variable for what the size of our input is, right? But that's not always the case. So for example, if we have an array that I give you, an n by n array, right? That we're going to say n, but what's the size of our input? How much information do I need to convey to you to give you that information? It's n squared, right? So that's the size of our input in that context, right? Or if I give you a graph, it's usually the number of vertices plus the number of edges. That's how big, how much space I would need to convey to you that graph, that information. Okay, so we compare how fast an algorithm is with respect to the size of the input, right? And if that, we will use the asymptotic notation. We have big O notation, which corresponds to upper bounds. We'll have omega, which corresponds to lower bounds. And we have theta, which corresponds to both, right? This thing is tight. It is bounded from above and below by a function of this form. Okay? Right? Kind of an abstract notion of how well this algorithm does. And so what we're going to use to measure time or efficiency, right, is something called asymptotic analysis. Anyone here understand what?
I don't know if you I think it's everywhere in actual program. Oh really? I don't know if you have heard of this or seen this, but this is what it was making me think of. It was an old show that I used to watch when I was a kid. It was the Big O. It was on Toonami. I guess that I don't know if this actually has to do with programming, but he's basically like he's Batman with a giant robot in like an old anime. But yeah, I used to watch this when I was a kid. Big O. Yeah. Yeah, that tripped me out when I was talking about that part. But I think I went back too far. I didn't mean to go back that far. I was like,
this thing is to compare how fast an algorithm is or what the size of our input is, right? But that's not always the case. So for example, if we have an array that I give you, an n by n array, right? That we're going to say n, but what's the size of our input? How much information do I need to convey to you to give you that information? It's n squared, right? So that's the size of our input in that context, right? Or if I give you a graph, it's usually the number of vertices plus the number of edges. That's how big, how much space I would need to convey to you that graph, that information. Okay, so we compare how fast an algorithm is with respect to the size of the input, right? And if that, we will use the asymptotic notation. We have big O notation, which corresponds to upper bounds. We'll have omega, which corresponds to lower bounds. And we have theta, which corresponds to both, right? This thing is tight. It is bounded from above and below by a function of this form. Okay? Now we have a couple common ways, a couple common functions that algorithms, their running time. We have a couple common functions that relate an algorithm's input size to its performance. Some things that we saw all the time. Can anyone give me some of those? Say again? Sorry. So like a function, I'm not asking this question well, but has anyone heard of a linear algorithm? A linear time algorithm, right? That's basically saying that the running time of my algorithm, performance of my algorithm, is linear with respect to the size of my input, right? Yeah. Say again? Like putting something in a list. Okay, so there's a lot behind that question that we'll go into later this week. But that's an example of if I do it in a silly way, I stick something in the middle of a list and I have to move everything, that's an operation that could take linear time, right? Okay. So linear time is a type of function. We've got a number of these. I'm going to start with this one. Does anyone know what this one is? Constant time. Okay. Basically, no matter how I change the input, the amount of time this running time, the performance of my algorithm takes, it doesn't really depend on that. Okay. The next one up is something like this. This is logarithmic time. Okay. We have theta n, which is linear, n log n, right? Sometimes we call this log linear, but we usually just say n log n. Okay. We have a quadratic running time. In general, if I have a constant power up here, right, it's n to the c for some constant. This is what we call polynomial time, right? As long as c is some constant. And this right here is what we mean by efficient in this class usually, right? In some other classes, right, when you have big data sets, maybe this is efficient, right? But in this class, generally what we mean is polynomial, and as you get down this thing, things are more and more efficient, okay? There's one class I'm going to talk to you about over here, which is something like, let's do this, 2 to the theta of n, right? Exponential time, this is some constant to a function of n that's, say, superlinear. That's going to be, pretty bad. Why is it pretty bad? If I were to plot some of these things as a function of n, right? Let's say I plot values of up to 1,000 on my n scale here. Okay? What does constant look like? Maybe this is 1,000 up here too. What does a constant look like? Looks like a line, right? It looks like a line over here somewhere. It could be as high as I want, but eventually anything that's an increasing function will get bigger than this, right? And on this scale, if I use log base 2 or some reasonable small constant, what does log look like? Well, let's do an easier one. What does linear look like? Yeah, this, right? That's what I saw a lot of you doing. Okay? That's linear. That's the kind of base that we're comparing everything against. What does log look like? Like this. Okay. But at this scale, right? At this scale, really, it's much closer to constant than linear. And actually, as n gets much, much larger, this almost looks like a straight line. It almost looks like a constant. So log is almost just as good as constant, right? What does exponential look like? It's the exact inverse of this thing, right? Right? It's almost an exact straight line going up, right? So this is crap. This is really good. Almost anything in this region over here is better, right? At least I'm gaining something. I'm able to not go up too high relative to my input size. So quadratic, I don't know, is something like this, and n log n is something like this. N log n, after a long time, really starts just looking linear with a constant multiplied in front of it, right? Okay, so these things good, that thing bad, okay? That's what that's trying to convey. All right, so how do we measure these things if I don't know what my fundamental operations are that my computer can use, right? So we need to define some kind of model of computation for what our computer is allowed to do in constant time, in a fixed amount of time, right? In general, what we use in this class is a machine called a word RAM, which we use for its theoretical brevity. All right, word RAM is kind of a loaded term. What do these things mean? It means I have, does someone know what RAM means? Random access memory, right? It means that I can randomly access different places in memory in constant time. That's the assumption of random access memory. Basically, what our model of a computer is you have memory, which is essentially just a string of bits. It's just a bunch of ones and zeros, right? And we have a computer, like a CPU, right? Which is really small. It can basically hold a small amount of information, but it can change that information, right? It can operate on that information, and it also has instructions to randomly access different places in memory, bring it into the CPU, act on it, and read it back. Does that make sense? But in general, we don't have an address for every bit in memory, every 0 and 1 in memory. We actually, does anyone know how modern computers are addressed? Yeah. Okay, so we're going to get there. Actually, what a modern computer is addressed in is bytes, okay, collections of 8 bits. So there's an address I have for every 8 bits in memory, consecutive 8 bits in memory. And so if I want to pull something into the CPU, I give it an address. It'll take some chunk, right, and bring it into the CPU, operate it on it, and spit it back, okay? How big is that chunk? This goes to the answer that you were asking, or saying, which is it's some sequence of some fixed number of bits, which we call a word, okay? A word is how big of a chunk that the CPU can take in from memory at a time and operate on, okay? In your computers, how big is that word size? 64 bits, right? That's how much I can operate on a time. When I was growing up, when I was your age, okay, my word size was 32 bits. And that actually was a problem for my computer because in order for me to be able to read to address in memory, I need to be able to store that address in my CPU, in a word, right? But if I have 32 bits, how many different addresses can I address? I have a limitation on the memory addresses I can address, right? So how many different memory addresses can I address with 32 bits? 2 to the 32, right? That makes sense. Well, if you do that calculation out, how big of a hard disk can I have to access? It's about 4 gigabytes, right? So in my day, all hard drives were limited to being partitioned. Even if you had a bigger than 4 gigabyte hard drive, I had to partition it into these 4 gigabyte chunks, which the computer could then read onto, right? That was very limiting, actually. That's a restriction. With 64 bits, what's my limitation on memory that I can address? Byte addressable. Turns out to be something like 20 exabytes. To put this in context, all data that Google stores on their servers, on all drives throughout the world, it's about 10. Right? So we're not going to run out of this limitation.
What the heck is an exabyte? I never heard of that. What the... An exabyte is a unit of data equal to 1,000,000 trillion bytes. What? So, byte versus, yeah, terabyte. I know what a terabyte is. Oh my god, 1 exabyte is how many? 1,000,000. It's 1,000,000 terabytes. Okay, that's alrighty.
Very soon, right? So what do we got? We've got a CPU. It can address memory. What are the operations I can do in this CPU? Generally, I have binary operations. I can compare two words in memory, and I can either do, integer arithmetic, kind of logical operations, bitwise operations, but we're not going to use those so much in this class. And I can read and write from an address in memory a word in constant time. Those are the operations that I have available to me on most CPUs. Some CPUs give you a little bit more power, but this is generally what we analyze algorithms with respect to, okay? But you'll notice that my CPU is only built to operate on a constant amount of information at once, generally 2 words in memory. An operation produces a third one, and I spit it out, right? It takes a constant amount of time to operate on a constant amount of memory. If I want to operate on a linear amount of memory, n things, how long is that going to take? Right? If I just want to read everything in that thing, it's going to take me linear time, right? Because I have to read every part of that thing. Okay? So in general, what we're going to do for the first half of this class, mostly, first 8 lectures anyway, is talk about data structures. And it's going to be concerned about not operating on a constant amount of data at a time, like our CPU is doing, but instead what it's going to do is store a large amount of data and support different operations on that data, okay? So if I had a record that I want to maintain to store those birthdays that we had before, I might use something like a static array, right, which you guys maybe are not familiar with if you have been working in Python as your only programming language, okay? Python has a lot of really interesting data structures like a list and a set and a dictionary and all these kinds of things that are actually not in this model. There's actually a lot of code between you and the computer, and it's not always clear how much time that interface is taking, right? And so what we're going to do starting on Thursday is talk about ways of storing a non-constant amount of information to make operations on that information faster. So just before you go, I just want to give you a quick overview of the class. To solve an algorithm problem in this class, we essentially have 2 different strategies. We can either reduce to using the solution to a problem we know how to solve, or we can design our own algorithm, which is going to be recursive in nature. We're going to either put stuff in the data structure, we're going to solve a sorting problem, or search in a graph. And then to design a recursive algorithm, we have various design paradigms. This is all in your notes, but this is essentially the structure of the class. We're going to spend quiz 1, the first 8 lectures, on data structures and sorting. Second quiz will be on shortest paths algorithms and graphs. And then the last one will be on dynamic programming. Okay, that's the end of the first lecture. Thanks for coming.
Man, that was a lot. They're just talking about how the algorithms work. Algorithms and computations. Some words I'm going to have to start remembering. Jesus. Yeah, I don't know. All that would have really helped long term. Yeah, that was a lot of, I don't know. mean, I get how he's explaining like how the algorithms work and everything, but I will admit there was a lot in there, like especially some of the terminology that he was using that like I'm not up to date with either, so that was kind of painful. Oh, Olivia fell asleep. Let's see what this thing is. Quiz 1 review. Oh god.
All right. Welcome everybody.
It's gonna be rough.
Everyone ready for the quiz?
No.
Quiz next week. Yes. I hope you all are here because you know that there's a quiz next week. Okay, so what is this quiz about? It's about what we've talked about so far in this class, of course. What is this class about? Someone remember from my first lecture? What is this class about? What are we trying to test you in this class?
Algorithms.
Algorithms, great. Also data structures, right? That's what the first part of this is. But really, it's to get you to solve computational problems. That's the first thing. Be able to argue to someone else that you actually did solve it, right? It's correct, right? That you chose something that's better than other things, that it's efficient, right? And that you can communicate those things to other people, right? Those are my big four that I try to get you guys to internalize. And so that's what our quizzes are going to try to evaluate you on, okay? And so aside from kind of some this nitty-gritty kind of stuff that we do at the beginning of the term, like talking about our model of computation, right? Our model and like asymptotics, asymptotics, is that right? Recurrences, right? Aside from these kind of basics, we kind of delve straight into algorithms, right? These are kind of like, almost definitions. We don't rely on these things very much. I mean, we rely on these things all the time, but it's kind of the mathematics that we use to talk about things, right? How can we even say how long this stuff takes unless we can reason, we can abstract away that this stuff is not on a real computer, this is kind of in our minds in a computer, and we're reasoning about these things based on the number of constant time operations this magical computer might have, so that, which is a pretty good representation of any of the computers you have, right, for certain assumptions, right? We're not gonna, there's not a lot of problem set questions. We had you talk about these things, like specifically. Usually they were part of some other problem, right? You had to describe the running time of this thing, and you might have had to solve a recurrence, and you might use master theorem, that kind of thing, right? Or we use asymptotics all the time, or you need to remember in our model, oh, it kind of matters how big of an integer I can store and do arithmetic on in constant time, right? So for that pset3 question you had at the end of the coding question, right? You wanted to hash things, and you need to argue that those things fit in a constant number of words, so that that could be done in constant time. A lot of you guys found canonicalizations, basically mapping to things that were exponentially large. So maybe multiplying a product of primes or something like that. And that would not be a good representation.
Looks like it is the wrong order to download in section. What do you mean? There should be a lecture videos tab. There's a correct order. There's lecture 2. Yeah, I can do this one. Are these in actual order or something? Oh, look, quiz 2 review. Wait, they weren't in order in the other one? What does this say? Structures and dynamic arrays.
Good morning. Welcome to 006, Introduction to Algorithms, Lecture 2. I am Eric Demain, and I love algorithms. Are you with me? Yeah. Today, we're not doing algorithms. No, we're doing data structures. It's okay. There's lots of algorithms in each data structure. It's like multiple algorithms for free. We're going to talk about sequences and sets and linked lists and dynamic arrays. Fairly simple data structures today. This is the beginning of several data structures we'll be talking about in the next few lectures. But before we actually start with one, let me tell you / remind you of the difference between an interface, which you might call an API if you're a programmer, or an ADT if you're an ancient algorithms person like me, versus a data structure. These are useful distinctions. The idea is that an interface says what you want to do. A data structure says how you do it. So you might call this a specification. And in the context of data structures, we're trying to store some data. So the interface will specify what data you can store. Whereas the data structure will give you an actual representation and tell you how to store it. This is pretty boring. Just storing data is really easy. You just throw it in a file or something. What makes it interesting is having operations on that data. So in the interface, you specify what the operations do, what operations are supported, and in some sense what they mean. And the data structure actually gives you algorithms. This is where the algorithms come in for how to support those operations. All right, so in this class, we're going to focus on two main interfaces and various special cases of them. So the idea is to separate what you want to do versus how to do it, because you can think of this as the problem statement. So last class, Jason talked about problems and defined what a problem was versus algorithmic solutions to the problem. And this is the analogous notion for data structures, where we want to maintain some data according to various operations. So the same problem can be solved by many different data structures, and we're going to see that. And different data structures are going to have different advantages. They might support some operations faster than others, and depending on what you actually use those data structures for, you choose the right data structure. But you can maintain the same interface. We're going to think about two data structures. One is called a set, and one is called a sequence. These are highly loaded terms. Set means something to a mathematician. It means something else to a Python programmer. Sequence, similarly. I guess there's not a Python sequence data type built in. The idea is we want to store n things. The things will be fairly arbitrary. Think of them as integers or strings. And on the one hand, we care about their values. And maybe we want to maintain them in sorted order and be able to search for a given value, which we'll call a key. And on the other hand, we care about representing a particular sequence that we care about. Maybe we want to represent the numbers 5, 2, 9, 7 in that order and store that. In Python, you could store that in a list, for example. And it will keep track of that order. And this is the first item, the second item, the last item. Today, we're going to be focusing on this sequence data structure, although at the end, I'll mention the interface for sets. But we're going to be actually solving sequences today. And in the next several lectures, we'll be bouncing back and forth between these. They're closely related, pretty abstract at the moment. On the other hand, we're going to have two main, let's call them data structure tools or approaches. One is arrays, and the other is pointers, pointer-based or linked data structures. You may have seen these. They're used a lot in programming, of course. But we're going to see both of these today. I'll come back to this sort of highlight in a moment. Let's jump into the sequence interface, which I conveniently have part of here. There's a few different levels of sequences that we might care about. I'm going to start with the static sequence interface. This is where the number of items doesn't change, though the actual items might. So here we have n items. I'm going to label them x0 to xn minus 1, as in Python. So the number of items is n. And the operations I want to support are build, length, iteration, get, and set. So what do these do? Build is how you get started. To build a data structure in this interface, you call build of x. Exactly how you specify x isn't too important, but the idea is I give you some items in some order. In Python, this would be an iterable. I'm going to want to also know its length. And I want to make a new data structure of size n, a new static sequence of size n that has those items in that order. So that's how you build one of these. Because somehow we have to specify n to this data structure, because n is not going to be allowed to change. I'm going to give you a length method. Methods are the object-oriented way of thinking of operations that your interface supports. So length will just return this fixed value n. Iter sequence, this is the sense in which we want to maintain the order. I want to be able to output x0 through xn minus 1 in the sequence order, in that specified order that they were built in, or that it was changed to. So this is going to iterate through all the items. So it's going to take at least linear time to output that. But more interesting is we can dynamically access anywhere in the middle of this sequence. We can get the ith item xi, given the value I, and we can change xi to a given new item. Okay, so that's called get at and set at. Pretty straightforward. This should remind you very closely of something, a data structure. So this is an interface. This is something I might want to solve. But what is the obvious data structure that solves this problem? Yeah. A list. In Python, it's called a list. I prefer to call it an array, but to each their own. We're going to use lists. List could mean many things. But the solution to this interface problem, the natural solution, is as what I'll call a static array. Jason mentioned these in lecture 1. It's a little tricky because there are no static arrays in Python. There are only dynamic arrays, which is something we will get to. But I want to talk about what is a static array really. And this relates to our notion of our model of computation, which Jason also talked about, which we call a word RAM. Remember? So the idea in word RAM is that your memory is an array of W-bit words. This is a bit circular. I'm going to define an array in terms of the word RAM, which is defined in terms of arrays. But I think you know the idea. So we have a big memory, which goes off to infinity maybe. It's divided into words. Each word here is W bits long. This is word 0, word 1, word 2. And you can access this array randomly, random access memory. So I can give you the number 5 and get 0, 1, 2, 3, 4, 5, the fifth word in this RAM. That's how actual memories work. You can access any of them equally quickly. Okay, so that's memory. And so what we want to do is when we say an array, we want this to be a consecutive chunk of memory. Let me get color. So let's say I have an array of size 4, and it lives here. Jason can't spell, but I can't count, so I think that's 4. We've got, so the array starts here, and it ends over here. It's of size 4. And it's consecutive, which means if I want to access the array at position, at index I, then this is the same thing as accessing my memory array at position wherever the array starts, which I'll call the address of the array. In Python, this is ID of array, plus I. Okay, this is just simple offset arithmetic. If I want to know the 0th item of the array, it's right here where it starts. The first item is 1 after that. The second item is 1 after that. So as long as I store my array consecutively in memory, I can access the array in constant time. I can do get at and set at as quickly as I can randomly access the memory and get a value or set a value, which we're assuming is constant time. So array access is constant time. Okay, this is what allows a static array to actually solve this problem in constant time per get at and set at operation. So this may seem simple, but we're really going to need this model and really rely on this model increasingly as we get to more interesting data structures. This is the first time we're actually needing it. Let's see. Length is also constant time. We're just going to store that number n along with its address. And build is going to take linear time. Iteration will take linear time. Okay, pretty straightforward. I guess one thing here when defining build, I need to introduce a little bit more of our model of computation, which is how do you create an array in the beginning? I claim I could do it in linear time, and that's just part of the model. So this is called the memory allocation model. There are a few possible choices here, but the cleanest one is just to assume that you can allocate an array of size n in theta n time. So it takes linear time to make an array of size n. You could imagine this being constant. It doesn't really matter much, but it does take work. And in particular, if you just allocate some chunk of memory, you have no idea whether it's initialized. So initializing that array to zeros will cost linear time. It won't really matter, constant versus linear, but a nice side effect of this model is that space, if you're just allocating arrays, the amount of space you use is at most the amount of time you use, or I guess big O of that. So that's a nice feature. It's pretty weird if you imagine, it's unrealistic to imagine you can allocate an array that's infinite size and then just use a few items out of it. That won't give you a good data structure. So we'll assume it costs to allocate memory. And OK, great, we solved the static sequence problem. Very simple, kind of boring. These are our optimal running times. Now, let's make it interesting. Make sure I didn't miss anything. And talk about, there is one thing I want to talk about in the word RAM. A side effect of this assumption that array access should take constant time and that accessing these positions in my memory should take constant time is that we need to assume W is at least log n or so. W, remember, is the machine word size. In real computers, this is currently 64 or 256 in some bizarre instructions. But we don't usually think of the machine as getting bigger over time. But you should think of the machine as getting bigger over time. This is a statement that says the word size has to grow with n. It might grow faster than log n, but it has to grow at least as fast as log n. Why do I say that? Because if I have n things that I'm dealing with, n here is the problem size. Maybe it's the array I'm trying to store, or whatever. If I'm having to deal with n things in my memory, at the very least, I need to be able to address them. I should be able to say, give me the ith one, and represent that number I in a word. Otherwise, because the machine is designed to only work with W-bit words in constant time, if I want to be able to access the ith word in constant time, I need a word size that's at least log n, just to address the n things in my input. So this is a totally reasonable assumption. It may seem weird, because you think of a real machine as having constant size. But a real machine has constant size RAM also. My machine has 24 gigs of RAM or whatever. That laptop has 8. But you don't think of that as changing over time. But of course, if you wanted to process a larger input, you would buy more RAM. So eventually, when our n's get really, really big, we're going to have to increase W just so we can address that RAM. That's the intuition here. But this is a way to bridge reality, which are fixed machines, with theory. In algorithms, we care about scalability for very large n. We want to know what that growth function is and ignore the lead constant factor. That's what asymptotic notation is all about. And for that, we need a notion of word size also changing in this asymptotic way. All right, that will be more important next week when we talk about hashing and why hashing is a reasonable thing to do. But let's move on to dynamic sequences, which is where things get interesting. So I have the update here. So we start with static sequences. So all of these operations are still something we want to support in a dynamic sequence, but we add 2 dynamic operations, somewhat controversial operations, exciting. I want to be able to insert in the middle of my sequence, and I want to be able to delete from the middle of my sequence. So here's my sequence, which I'm going to think of in a picture. I'm going to draw it as an array, but it's stored however it's stored. We don't know. This is an interface, not an implementation. So we have x0, x1, x2, x3. And let's say I insert at position 2. So position 2 is here. So I come in with my new x. And I would like x to be the new x2, but I don't want to lose any information. If I did set at 2, then I would erase this and replace it with x. But I want to do insert at, which means all of these guys conceptually are going to shift over by 1 in terms of their indices. So then I would get this picture that's 1 bigger. And now I've got the new x. I've got what was the old x2, which I hesitate to call x2 because that's its old name, not its new name. I'm going to draw arrows to say these guys get copied over. These ones are definitely unchanged. Our new x2, which I'll call x2 prime, is x. This is x3 prime, x4 prime, and so on. I want to be careful here, and of course the new n prime is n plus 1. I want to be careful about the labeling, because the key, what makes insert at interesting, is that later when I call get it's with the new indexing. So previously, if I did get at 2, I would get this value. And afterwards, if I did get at 2, I get the new value. If I did get at 3 down here, I get the value that used to be x2. Okay? That's maybe hard to track. But this is a useful, conceptually very useful thing to do, especially when you're inserting or deleting at the ends. So we're going to define, in particular, insert and delete first and last. These are sometimes given, if you have an insert, it has an x. If you do a delete, it has no argument. So this means insert at the beginning of the array, which would be like adding it here. And insert last means adding it on here. So insert last doesn't change the indices of any of the old items. That's a nice feature of insert last. Insert first changes all of them. They all get incremented by 1. And we're also interested in the similar things here. We could do get first or last, or set first or last. Okay, which are the obvious special cases of get at and set at. Now, these special cases are particularly interesting in an algorithms context. If you were a mathematician, you would say, well, why do I even bother this? This is just shorthand for a particular call to get or set. But what makes it interesting from a data structures perspective is that we care about algorithms for supporting these operations, and maybe the algorithm for supporting get first or set first, or in particular insert first or insert last, might be more efficient. Maybe we can solve this problem better than we can solve insert at. So while ideally we could solve the entire dynamic sequence interface constant time per operation, that's not actually possible. You can prove that. But special cases of it where we're just inserting and deleting from the ends say we can do that. So that's why it's interesting to introduce special cases that we care about. Cool, that's the definition of the dynamic sequence interface. Now we're going to actually solve it. So our first data structure for this is called linked lists. You've probably seen linked lists before at some point, but the main new part here is we're going to actually analyze them and see how efficiently they implement all these operations we might care about. So first, review. What is a linked list? We store our items in a bunch of nodes. Each node has an item in it and a next field. So you could think of these as class objects with two class variables, the item and the next pointer. And we assemble those into this kind of structure where we store in the item fields, we're going to store the actual values that we want to represent in our sequence, x0 through xn minus 1, in order. And then we're going to use the next pointers to link these all together in that order. So the next pointers are what actually give us the order. And in addition, we're going to keep track of what's called the head of the list. So the data structure is going to be represented by head. If you wanted to, you could also store length. So this could be the data structure itself. And it's pointing to all of these types of data structures. Notice we've just seen an array-based data structure, which is just a static array. And we've seen a pointer-based data structure. And we're relying on the fact that pointers can be stored in a single word, which means we can dereference them. We can see what's on the other side of the pointer in constant time in our word RAM model. In reality, each of these nodes is stored somewhere in the array of the computer. So maybe each one is 2 words long, so maybe one node is, the first node is here, maybe the second node is here, the third node is here. They're in some arbitrary order. We're using this fact that we can allocate an array of size n in linear time. In this case, we're going to have arrays of size 2. We can just say, oh, please give me a new array of size 2. And that will make us one of these nodes. And then we're storing pointers. Pointers are just indices into the giant memory array. They're just, what is the address of this little array? Okay? If you've ever wondered how pointers are implemented, they're just numbers that say where in memory is this thing over here. And in memory, they're in arbitrary order. This is really nice because it's easy to manipulate the order of a linked list without actually physically moving nodes around, whereas arrays are problematic. Maybe it's worth mentioning, let's start analyzing things. So we care about these dynamic sequence operations, and we could try to apply it to the static array data structure, or we could try to, we could try to implement these operations in a static array. It's possible, just not going to be very good. And we can try to implement it with linked lists. And it's also not going to be that great. Let's go over here. Our goal is the next data structure, which is dynamic arrays. But linked lists and static arrays each have their advantages. So let's first analyze dynamic sequence operations. First on a static array. And then on a linked list. So on a static array, I think you all see, if I try to insert at the beginning of the static array, that's kind of the worst case. If I insert first, then everybody has to shift over. If I'm going to maintain this invariant, that the ith item in the array represents, I guess I didn't write it anywhere here, maybe here. Static array, we're going to maintain this invariant that a of I represents xi. Okay? If I want to maintain that at all times, when I insert a new thing in the front, because the indices of all the previous items change, I have to spend time to copy those over. You can do it in linear time, but no better. Okay, so static array, insert and delete anywhere, cost theta n time. Actually, for 2 reasons. Reason number 1 is that if we're near the front, then we have to do shifting. Okay, what about insert or delete the last element of an array? Is that any easier? Because then, if I insert the very last element, none of the indices change. I'm just adding a new element. So I don't have to do shifting. So can I do insert and delete last in constant time in a static array? Yeah? No, because the size is constant. So our model is that, remember our allocation model is that we can allocate a static array of size n, but it's just of size n. I can't just say, please make it bigger by 1. I need space to store this extra element. And if you think about where things are in memory, when you call to this memory allocator, which is part of your operating system, you say, please give me a chunk of memory, it's going to place them in various places in memory, and some of them might be next to each other. So if I try to grow this array by 1, there might already be something there, and that's not possible without first shifting. So even though in the array I don't have to do any shifting, in memory I might have to do shifting. And that's outside the model. So we're going to stick to this model of just, you can allocate memory, you can also deallocate memory, just to keep space usage small. But the only way to get more space is to ask for a new array, and that new array won't be contiguous to your old one. So, question? What is a dynamic array will be the next topic, so maybe we'll come back to that. Yeah? Okay, so in a static array, you're just not allowed to make it bigger, and so you have to allocate a new array, which we say takes linear time. Even if allocating the new array didn't take linear time, you have to copy all the elements over from the old array to the new one, then you can throw away the old one. So just the copying from an array of size n to an array of size n plus 1, that will take linear time. So static arrays are really bad for dynamic operations, no surprise, but you could do them, okay? That's static array. Now linked lists are going to be almost the opposite. Well, almost. So if we store the length, okay, we can compute the length of the array very quickly. We can insert and delete at the front really efficiently. If I want to add a new item at the as a new first item, then what do? I allocate a new node, which I'll call x. So this is insert first of x. I'll allocate a new array of size 2. I'm going to change, let me do it in red. I'm going to change this head pointer. Maybe I should do that later. So I'm going to set the next pointer here to this one. And then I'm going to change this head pointer to point to here. And boom, now I've got a linked list. Again, we don't know anything about the order in memory of these lists. We just care about the order that's represented implicitly by following the next pointers repeatedly. So now I've got a new list that has x in front, and then x0, and then x1, and so on. So insert and delete, first at least, are really efficient. We won't get much more than that. But in a linked list, insert and delete.
Well, I mean, I don't really know. Okay, so he's talking about static arrays and dynamic arrays. I don't really know what an array is, but I'm kind of guessing the concept is a static array is a piece of information that if you're changing the information, you have to delete it and replace it. You have to copy it. You have to copy it over if you change it, and then delete it. And dynamic array, but I don't really understand what the array thing is, because I know like static and dynamic. I mean, static is something that doesn't change, and dynamic is something that changes. I mean, that's like the terms that we used in the oil field. It was an array. An array is the array object, as with arrays in programming languages, enables storing a collection of multiple items under a single variable name. So, like a variable is a array. Because I know what a variable is. And has members of performing was an array. Do they have a quick I'll watch like a crazy long video about it or something.
So hello and welcome everyone. So in this video, I am going to explain the most basic and fundamental data structure, that is.
Array is essentially a chunk of memory in which you store things, right? Yeah, that's what I was thinking it was. I don't know if an array is any particular specific, like, I mean, so like when you create a variable and you tell it like you're on Python, you tell Python like this variable means this, then that would be an array, right? One dimension terminology vector example. But yeah, it's basically a chunk of information. Array variable index of the element to be assessed. So the array is the whole thing. And this you're selecting that first. Yeah, because I know whenever you have like a variable and a variable's like a string and whatever, you can put 0 to select the very first part of it. But I mean, a static array, I don't know how static arrays and dynamic arrays really work in like coding. I don't know how you specifically make that. I mean, is that just how, is he talking about how like certain coding things work and stuff? Because I get this insert and delete. It costs time because you have to shift and copy the information over and then delete the old information. It means fixed size. And what dynamic array? And what is dynamic array? Because dynamic array, what he was, is that what he, I thought the dynamic array was the one where he was talking about how you have the outer chunks with what you have, so you, when you put something in a spot, it shifts over. But this, oh, I don't know, he put shifting here, but I thought the static array doesn't shift. That's the dynamic array that scoots the information over. It still doesn't entirely, like, it's kind of, in the dynamic array, you can change the size, so essentially you can add or delete items. I mean, you can't change the size because it already takes up more space than it needs. Because that also doesn't totally make sense for it to be able to just change size. You can add or delete items. So in static array, if you do any changes, you're forced to copy and delete the old chunk of information. And means that you can implement a dynamic array using a static one. Alright, I'm gonna go to the restroom real quick. It means that you can implement it. And to do that, you essentially recreate the whole array Yeah, but you read so if but you only recreate a static array, right? Or when you go from a static array to a dynamic array, you recreate the whole array when you add or delete an item. And then I don't know what the lind list is at all, honestly. I don't know that at all what he's talking about there. Lind list. I don't even know if I'm spelling that right. Lind is a renowned chocolate brand. That's not what I meant. Let's see. A linked list. A linked list is a linear data structure made of nodes connected using pointers. Each node has data. I thought a node was like a single piece of data, like a byte or something. I don't. God damn. I looked at some of this stuff up a long time ago, but each node has data. The value stored in the node. What nodes are not stored in contingent arrays? They can be anywhere in memory. To access the node, we start from the head. There's a bunch of arrays of size 2 that are placed randomly in memory. Types of links list. The first item is the value, and the second is where to find the next one. That sounds really confusing. And the static array, the first item is the value, and the second is where to find the next one. What is that? That sounds more confusing. Jesus. I thought a node was like a physical part of the computer, like inside the node. Like I thought that was like a physical part, like I mean not the program. A node is a fundamental element that serves as a connection point within a network of data or structure. It's a connection point. Nodes are essentially for facilitate. Contains data and a pointer to the next node. This is, man. I need someone to, like, draw this stuff out for me. Because this is, man. It's like a lot of words I'm not used to hearing.
First, our constant time.
I need something that's like. I mean, is. The memory is a big static array. A node contains a value and an index of the next node. So a node contains value, and so I mean, is it talking about like when you create a variable, and that variable has something like a string in it? Is like, I mean, would a node be like one of those strings, like one of the letters in the string connecting to the next one, or am I thinking about this too much the wrong way? Explain in 6 minutes. That's a long time. What is it? Explain in 2 minutes.
Let's talk about Node.js. What is it? Why is it important? And how you can get started today. All of that and more.
That's not the software. They have like a quicker one.
I love this sequel.
Data Grip allows you to write SQL you'll love. Enjoy powerful code completion.
Got a variety of programming concepts. Hello everyone, and welcome to the first video in the brand new Data Structures and Algorithms in Java series. We'll look at a variety of programming concepts and put them into practice with a wide range.
It will all be about node, not actual nodes, and yeah, that's what I'm thinking. I'm like, who's the god dang? I can't find the no. I don't even know what DSS stands for. Oh my god, it is better to look up what's. DSS decision support system. I think I saw something about DSS. This is killing me. Data structures.
Hey everyone, welcome to my brand new linked list tutorial. Let's begin. Before we start, let's go over the basic timeline of this video. So the timeline is split up into 4 parts. What are linked lists?
I don't care.
Let's go ahead and define what a linked list is. A linked list is simply just an abstract data structure. An abstract data structure simply means that it's built on top of regular data structures in the form of a class or a structure. And it uses basic data structures like an integer and pointers to make it work. And like other data structures, it's used to store data, for example, an integer. But how do linked lists exactly work? So the way a linked list works, as you can see over here, is that there's a specific node. A linked list is made up of a bunch of nodes. Each node contains an integer value, or a string, but usually an integer, as well as a pointer to another memory address. As you can see over here, there's a memory address for this specific node, and it points to another node. This node will follow the exact same architecture. However, in the scenario of which there is no next node, it's going to remain as null. And if there is a node that is at the top, we call that the head node. And if there is a node where the next pointer is null, also known as the end of the node, is called the tail of our node. In order to implement your own linked list in your language, make a class or a struct, and simply have the two parameters of an integer as well as a next node, which is simply just going to be the same data type as the struct or the class. And boom, we've now created our very own linked list. Now it's time for the million-dollar question. How do you reveal as a next node your own linked list in your language, make a class or a struct, and simply have the two parameters of an integer as well as a next node, which is simply just going to be the same data type as the struct or the class?
I don't even know what he's trying to say. What is he saying? So an integer like 1 is a node. What is it saying? Node next? Integer x. I'm trying to figure out a way to understand this. Like, if I put 12, so does that mean that's a node and that's a node? A class is when you combine several variables into one variable. Yeah, but I'm still trying to figure. Oh wait, class node. This is when you combine several variables into one variable. Oh. Why would you? How do you? What? When you combine several. Okay. Well. But a node is like that. Is that's one node, right? I don't think there are pointers in Python. So he's just talking about that other thing, the C thing or whatever it's called. So Python doesn't work like that. It's the other one that works like that, the C, whatever that C one's called. Python hides it inside. Hides the node inside. That doesn't make any sense. What? Python hides the nodes. Oh my god, we already got Visual Studio Code. Oh, it's not you. It's my computer. I was messing with too much at one time. I probably need to do an update or something. Honestly. That's usually what happens when it starts having issues. Oh, it's always so annoying. I was trying to figure it out though. So, but you were saying Python doesn't use nodes like that. Only C uses nodes like that. In C, you have to do it manually. I don't even know how to use that program. Is it just called C? I have it right here, but I don't really like. I can't do it to do. I can't. I don't know how to use it at all. That's not even working right. GCC is not recognized as an internal or external command operable program or batch. See, but I got this on JavaScript. I can run that, but in C, I don't know what I'm doing wrong for this one. No, nah, my computer was being a butthead. You need to download a compiler for, on this side of things. I mean, can I do it through here? Extensions? I mean, I have Code Runner already. I thought that's what Code Runner does. And compiler. How do I download a compiler? I don't even know. Oh, that's probably my issues in video. Ugh. Maybe I never used Code Runner, so I can't tell. Yeah, I don't. I mean, it runs for JavaScript. I didn't use it for JavaScript. Did it do it? No. God, why isn't my freaking video working? That's so annoying. I think my computer needs to restart with that crap. It could be enough to get the gist of it. Yeah, but so nodes are the only, but I still don't like. It's still really confusing.
And boom, we've now created our very own linked list. Now it's time for the million-dollar question. How do you reverse a linked list? For this question, let's go ahead and assume we have a linked list with 1 pointing to 2, 2 to 3, and then 3 to null. How can we go ahead and reverse this in the other way? The 3 things that we're going to want to do first is make 3 nodes. We're going to make a node for current node, the previous node, and the next node. Now, initially, these values for the previous and next node will be null. So the first thing you will do is go ahead and take our current node and point it to the next node. After that, what you're going to do is take your next node and point it to the previous node. By doing so, we point our second node to our first node. After that, point the previous node to the current value of the node. By doing so, we've now reversed it so that point in node 2 points to node 1. By repeating this process over and over again, throughout the entire list, we can reverse the entire linked list completely. Now let's go ahead and view a pseudocode example of what I'm trying to explain. The first thing we're going to want to do is go ahead and create 3 variables. Current node, which will initially point to our head node, the previous node, which is for now null, and the next node, which is also null. The next thing we're going to do is create a while loop in which the current value of the node cannot be null. In the case that it's null, that means we've reached the end of our list. Next, we point our next node to...
Did you get to classes in Python? No. I don't even know what class... You said classes are when you put variables together. Then it's a class. Is multiple variables. Like a school of fish. There's fish. Fish are variables. And when you have a school of fish, you have a class of variables. Is that the right thing or no?
So that's cool. However, everything else is going to be slow. If I want to get the 10th item in a linked list, I have to follow these pointers 10 times. I go 0, 1, 2, 3, and so on. Follow 10 next pointers, and I'll get the 10th item. Accessing the ith item is going to take order I time.
How long have you been doing this?
I'm trying to do it as much as I can.
But how long have you been doing it?
All day.
So, for a couple hours?
Yeah.
Oh. But where does it say how many hours you've been doing it?
That doesn't.
Oh. Okay.
Well.
Look what I made. I still need to make the head.
So you're trying to draw some wings or something on it?
I was, but I decided to stop because, like, I tried to do dragon wings, but it didn't really turn out well. And I tried to do, like, bird wings, but I didn't want to, so I just decided to not do it.
Oh. Well.
But I was telling myself that I can get better at doing it in time.
Yeah, that's the most positive way to do it.
Just practice and you'll get better.
Be positive about it.
Yeah.
Is Olivia still asleep?
She woke up. I don't know if she's still awake.
Oh.
I gotta check. I love her.
I love you too.
So,
Oh. Well, it's 10 o'clock. Hopefully she stays asleep.
Get and set at. Need I time, which in the worst case is theta n. Okay, so we have sort of complementary data structures here. On the one hand, a static array can do constant time get at, set at, so it's very fast at the random access aspect because it's an array. Linked lists are very bad at random access, but they're better at being dynamic. We can insert and delete at the beginning, at least, in constant time. Now, if we want to actually insert and delete at a particular position, that's still hard because we have to walk to that position. Even inserting and deleting at the end of the list is hard, although that's fixable. And maybe I'll leave that for problem session or problem set. But so here's a small puzzle. Suppose you wanted to solve get last efficiently in a linked list. How would you solve that in constant time? Yeah. Doubly linked list is a good idea, but actually not the right answer. That's an answer to the next question I might ask. Yeah. Store a pointer to the last element. That's all we need here. And often a doubly linked list has this. I usually call this the tail, head and tail. And if you always just store a pointer to the last list, this is what we call data structure augmentation, where we add some extra information to the data structure, and we have to keep it up to date all the time. So if we do an insert last or something, insert last also becomes easy because I can just add a new node here and update the pointer here. Delete last is trickier. That's where you need a doubly linked list. But whenever I add something to the end of this list, I have to update the tail pointer also. As long as I maintain this, now suddenly get last is fast in constant time. So linked lists are great if you're working on the ends, even dynamically. Arrays are great if you're doing random.
So I think what's like confusing, so this doesn't pertain as much to Python as it does to like more of the complex coding, like using the C1 or whatever. But like in Python you won't see any of this. Is that what this basically like? This is confusing. Very, very confusing.
Do you like the body that I made?
Okay. Python implements all of that inside and you don't see that. So that's why Python's easier, because it doesn't use all this stuff that they're talking about. It kind of just, it's more user friendly, whereas these other things are more strict and very basic to how the computer actually works. That is why starting with low level languages might be a good idea, because you will eventually get to all this stuff, and these languages force you to learn it. Yeah. Well, I mean, I at least had to start somewhere, and Python's the easiest, so that's the other reason I was learning Python, was just because, I mean, we gotta have some sort of stepping stone, so. But this is making me want to learn, like, the other coding, but, like, is Python the only one that doesn't work like this? Or we had to manually implement all these data structures in C++ before we could use the already implemented solutions on our first year. And C++. So is C++ not like that anymore? Or do you not have to manually do all that work in it anymore? It's just understanding, like, I guess it does a lot of the stuff for you now, but that's probably why this ain't making a whole lot of sense, is because you don't see this stuff, especially, like, all I've been doing is messing with Python for a little bit, and you don't see any of this going on in Python.
Access and nothing dynamic, nothing adding or deleting at the ends or in the middle. Okay, so our final goal for today is to get sort of the best of both.
So like Java or JavaScript or whatever, is JavaScript kind of like that?
Worlds with dynamic arrays. We're going to try to get all the good running times of linked lists and all the good running times of static arrays. We won't get quite all of them, but most of them. And in some sense, another way to describe what these introductory lectures are about is telling you about how Python is implemented. So what we're going to talk about next, dynamic arrays, I've alluded to many times, but these are what Python calls lists. So you don't have to implement a dynamic array by hand because it's already built into many fancy new languages for free, because they're so darn useful. This lecture is about how these are actually implemented and why they're efficient. And in recitation notes, you'll see how to actually implement them if all you had were static arrays. But luckily, we have dynamic arrays, so we don't have to actually implement them. But inside the Python interpreter, this is exactly what's happening. Okay, so the idea is to relax the constraint, or the invariant, whatever, that the size of the array we use equals n, which is the number of items in the sequence. Okay, remember in the sequence problem, we're supposed to represent n items. With a static array, we allocated an array of size exactly n. So let's relax that. Let's not make it exactly n. Let's make it roughly n. How roughly? You can think about for a while. But from an algorithm's perspective, usually when we say roughly, we mean throw away constant factors. And that turns out to be the right answer here. It's not always the right answer. But we're going to enforce that the size of the array is theta n. Probably also greater than or equal to n. 0.5 n would not be very helpful. So it's going to be at least n. And it's going to be at most some constant times n. 2n, 10n, 1.1 times n. Any of these constants will work. I'm going to use 2n here, but there are lots of options. And now, things almost work for free. There's going to be one subtlety here. And I'm going to focus on, we're still going to maintain that the ith item of the array represents xi. Okay, so this data structure, let me draw a picture. So we've got an array of some size. the first few items are used to store the sequence, but then there's going to be some blank ones at the end. Okay, maybe we'll keep track of this.
You could at least rinse it all. Just
So the data structure itself is going to have an array, and it's going to have a length, something like this. So we're also going to keep track of the length. So we know that the first length items are where their data is, and the remainder are meaningless. Okay, so now if I want to go and do an insert last, what do? I just go to a of length and set it to x. And then I increment length. Boom, easy, constant time, yeah. How do you know you have enough room? Indeed, I don't. This was an incorrect algorithm. But it's usually correct. As long as I have extra space, this is all I need to do for insert last. But I'm also going to store the size of the array. This is the actual, this whole thing is size, and this part is length. So length is always going to be less than or equal to size. And so there's a problem if length equals size, then I don't have any space. Okay? Just add to the end, unless n equals size. I'm using n and length for the same thing. So length here is the same as n. That's our actual number of things we're trying to represent. And size, this is great. This is the interface size. This is what we're trying to represent. And this is the representation size. This is the size of my array. These are the number of items I'm trying to store in that array. Okay, this is the interface versus data structure. Here's the interface. Here's the data structure. Okay, cool. What do I do in the case when n equals size? I'm going to have to make my array bigger. Okay, this should sound just like static arrays. With static arrays, we made our array bigger every time we inserted. And that was this linear cost of allocation. We're going to do that sometimes. With static arrays, we had to do it every single time because size equaled n. Now we have some flexibility. We're only going to do it sometimes. It's like cookies are a sometimes food, apparently, according to modern Cookie Monster. I don't understand. But if n equals size, we're going to allocate a new array of size. Any suggestions? Bigger. I like it. Greater than size. How much bigger? Twice. Five things. Size plus 5? Come on, Jason. Trolling me. All right, so there are a couple of natural choices here. One is a constant factor larger. You could use 1.1 or 1.01 or 2 or 5 or 10. They'll all work. Or you could use Jason's trolling answer of size plus a constant, like 5. Why is this bad? Yeah. You'll have to do it again. You'll have to resize frequently. When? 5 steps later. So in the original static array, we were reallocating every single time. That's like n plus 1. If we do n plus 5, that really doesn't change things if we ignore constant factors. Now we'll have to spend linear time every 5 steps instead of linear time every 1 step. That's still linear time per operation. It's just we're changing the constant factor. Okay? Whereas 2 times size, well, now we have to think a little bit harder. Let's just think about the case where we're inserting at the end of an array. So let's say we do n insert last from an empty array. When do we resize? Well, at the beginning, I guess I didn't say what we do for an empty array. Let's say size equals 1. So we can insert one item for free. As soon as we insert the second item, then we have to resize. That seems bad. Immediately we have to resize. Then we insert the third item. OK, now let's draw a picture. So we start with one item. We fill it up. Then we grow to size 2, because that's twice 1. Then we fill it up. Immediately we have to resize again. But now we start to get some benefit. Now we have size 4. And so we can insert 2 items before we have to resize. And now we're size 8. And we get to insert 4 items before we refill. So this is going to resize. And again, resizes are expensive both because we have to pay to allocate the new array. I drew it as just extending it. But in fact, we're creating a whole new array. And then we have to copy all of the items over. So there's the allocation cost and then the copying cost. So it's linear either way. But we're going to resize at n equals 1, 2, 4, 8, 16. You know this sequence. All the powers of 2, because we're doubling. Right? That is exactly powers of 2. So we pay a linear cost. So this resize cost, the allocation and the copying, is going to be, it's linear each time. So it's 1 plus 2 plus 4 plus 8 plus 16. Okay, really I should write this as sum from I equals 1 to roughly log n, log base 2 of n is LG, of 2 to the I. Okay, if you want a terminus here, it's roughly n. It's actually the previous power of 2 of n or something. Okay, but that won't matter. That'll just affect things by a constant factor. What is the sum of 2 to the I? This is a geometric series. Anyone know the answer? Yeah.
Hippie John Travolta.
2 to the
I never remember what John
top limit,
Travolta looks like. I feel like
plus 1 minus
you
1.
did tell me that, but I don't remember. This is John Travolta. Oh, hey, that dude from them old movies. What was that one movie where he's like partying with it? He's like the boss dude or whatever. He's partying with that one. He had to watch the boss's daughter or something. God, what was that movie? was called. Oh my god, it should be like the first movie popping up, and I don't know how it's not. Pulp Fiction. Oh my god, that's what I was thinking of. That's so terrible. I'm struggling.
Yeah, so this is the identity. Sum of 2 to the I from I equals 1 to k is 2 to the k plus 1 minus 1. So the plus 1's upstairs, minus 1's downstairs. An easy way to remember this is if you think in binary, as we all should, we're computer scientists. 2 to the I means you set the ith bit to 1. So here's a bit string. This is the ith bit. This is 2 to the I, with zeros down here. If I sum them all up, what that means is I'm putting 1s here. Okay? And if you think about what this means, this is up to k from 0. Sorry, I should do 0 to be proper. If I write, so that's the left-hand side. The right-hand side is 2 to the k plus 1, which is a 1 here, and the rest zeros. So if you know your binary arithmetic, you subtract. If you add 1 to this, you get this. Or if you subtract 1 from this, you get this. Okay, this is why this identity holds. Or the higher level thing is to say, oh, this is a geometric series. So I know, you should know this, I'm telling you now. Geometric series are dominated by the last term, the biggest term. If you have any series you can identify as geometric, which means it's growing at least exponentially, then in terms of theta notation, you can just look at the last term and put a theta around it, and you're done. So this is theta, the last term, like 2 to the log n, which is theta n. Cool. Linear time. Linear time for all of my operations. I'm doing n operations here, and I spend linear total time to do all the resizing. That's good. That's like constant each, kind of. The kind of is an important notion, which we call amortization. So I want to say an operation takes t of n amortized time if, let's say, any k of those operations take at most k times t of n time. This is a little bit sloppy, but be good enough. So the idea is here, if this works for n or k, to do n operations from an empty array here takes linear time, which means I would call this constant amortized. Amortized means a particular kind of averaging. Averaging over the sequence of operations. So while individual operations will be expensive, one near the end, when I have to resize the array, is going to take linear time just for that one operation. But most of the operations are cheap. Most of them are constant. So I can think of charging that high cost to all of the other operations that made it happen. And so this is averaging over the operation sequence. Every insert last over there only takes constant time on average over the sequence of operations that we do. And so it's almost constant. It's not quite as good as constant worst case, but it's almost as good, and it's as good as you could hope to do in this dynamic array allocation model. Let me put this into a table, and you'll find these in the lecture notes also. So we have on the top the main operations of the sequence interface, which we will revisit in lecture 7. We'll see some other data structures for this. Get at and set at in the first column, insert and delete first, insert and delete last, insert and delete at an arbitrary position. So we've seen 3 data structures now. Arrays were really good at get at, set at. They took constant time. That's the blue one. We're omitting the thetas here. All the other operations took linear time no matter where they were. Linked lists were really good at insert and delete first. They took constant time, but everything else took linear time in the worst case. These new dynamic arrays achieve get at and set at in constant time because they maintain this invariant here, that a of I equals xi. So we can still do gets and set at quickly. And we also just showed that insert last is constant amortized. Delete last, you don't have to resize the array. You could just decrease length, and boom, you've deleted the last item. It's not so satisfying because if you insert n items and then delete n items, you'll still have an array of size theta n, even though your current value of n is 0. You can get around that with a little bit more trickery, which are described in the lecture notes, but it's beyond we're only going to do very simple amortized analysis in this class. To prove that that algorithm is also constant amortized, which it is, you'll see in 046, or you can find it in the CLRS book. That's it for today.
I'm Jason. Hopefully you guys saw me on Tuesday. This is our first ever 6006 problem session that we'll be having on Fridays this term. It's really an experiment. We've never done this before. But one of the things that we were discussed while preparing for this class is that we have two different methods of instruction formally, usually, in this class. A lecture, which is there to present you with the fundamental material, the data structures and the algorithms that are kind of the base, the foundation of how you will be approaching problems in this class. And then the problem sets that you will work on are applications of that material. But there's usually a much different feel between those problems that we'll give you than the underlying foundational material, right? So the application of that material will feel very different. And a lot of times there are tricks to approaching the problems or ways of approaching the problems that you kind of just have to figure out by working on the problems, sometimes going to office hours. But what we wanted to do this term was to, since we had the opportunity to be recorded by OCW, was to record us going through some problems that we've had on problem sets in the past, so you could see how we would approach working on these problems that you'll be working on, at least in a similar vein. So that's the goal of these problem sessions. In the past, for OCW, we have recorded a recitation, but we felt that that was a little less useful to you guys because recitation is meant for interaction, questions, one-on-one questions. We wanted to be a safe space for you guys to interact with the material in a smaller environment that might not be recorded. So that's the goal of these sessions that we'll be doing on Fridays. Any questions about what we're going to be doing today? Okay, so we do have a handout up here by the door, which we may or may not have in the future. This is all an experiment, so you'll have to work with us as we figure this stuff out. They were posted on LMOD about an hour before this session. We'll try to keep that as a standard. But it just shows you the questions we'll work on today in the session. It won't necessarily be the entire, it isn't just the problem set from last term. It's a selection of problems from previous terms, and some of them have been edited to be maybe a little shorter and things like that. So what we're going to do is just go through the problems one by one. I'll try to just kind of show you how I'm approaching the problems. But at any point, if you want to, you can ask questions. That's fine. OK? All right. So the first question we have has a setup that's very similar to what you will have on your PSET 1. It's essentially saying that it is usually many parts. This has two parts, an A part and a D part. I've omitted a B and a C that was on last term's problem set. and it has 5 functions each, and you're trying to order them increasing based on their asymptotic behavior. So here are the functions that we have. Maybe I'll stick it up instead. All right, so we have a few sets of functions, and we just want to order them. And some of the functions may be asymptotically equivalent, right? In which case, when we are ordering these things, we're going to put those numbers in a set. So what we have as an example are 3 functions, n, root n, and n plus root n. This is 1, 2, 3. And what we're going to ask you to do is order those functions based on their asymptotic complexity. So hopefully you guys can get this one. Which one's the slowest growth in terms? Root n. So number 2. So if we say f of 2 will be our first one. And then how about the other 2? They're the same. They're both order n, right? So we would put in set brackets f1 and f3. On your problem set, if you put just 2 and 1 and 3 here, that would probably be fine. Okay? But if you were to put 2 over here, or not have these curly braces around here, those would not be correct, and you'd get points marked off. Does that make sense? Okay, so we're going to approach the first set of problems, first set of functions, which is a little different than the second set of functions. Hopefully this one's a little easier. One of the common approaches that I have in going through these things, some of these are in a form that is hard for me to tell how they would compare to other things. Actually, most of these are fine, but in general, can anyone just by eyeballing tell me an order that works for them? Yeah? Okay. This is a little difficult to do on the spot with 5 functions.
Yeah, a little iffy about F1, but
okay.
F5 is definitely smaller than F2.
Okay.
Smaller than F3, which is smaller than F4.
Okay.
And F1 is iffy.
Okay, great. That's excellent. So what we've got here is on F2, F3, and F5, we kind of have this n leading term. If we factor an n out of that, then we're comparing log with a, basically we look over here at the polynomial function, right? This one's smallest out of them, and then the log factor is smaller than a polynomial factor, right? Log grows slower than linear, right? And so this guy is smaller than F2, is smaller than F3. That's great that your colleague said. In general, hopefully you proved in recitation Wednesday, this nice fact, I guess, that A is less than asymptotically, this polynomial, this log n to any power is asymptotically less than any polynomial for any positive a and b. And in particular, there's actually a stronger thing you can say, which is little o. Did you guys talk about little o in recitation at all? Probably not. It's kind of the same as big O, except is big O minus theta, right? So things that are asymptotically equivalent are not going to be included in this set. So actually, these things are strictly asymptotic, grow strictly asymptotically slower than any polynomial. Does that make sense? Okay, so knowing this identity, right, or this relation, can we say anything about F1?
Man, this is
Someone,
really
maybe someone else?
God. I don't know. Looks like they put this method in their course. Yeah, I don't even know what he's talking about. I don't even know what the F1, F2, F3, like, I don't even know what none of that is. Is that just part of other stuff that's not part of Python? We had it as part of the algorithm course. I mean, but does it have to do with coding, or is it just like part of just the way that, I don't even know, dude. This is like so confusing. Like I don't even know where he's like going with all this, or how some things are I don't know what the F1s through F5 stuff is, or I don't know any of that. This is just like some crazy way out there information I'm not even close to. I don't know. I need something simpler that's breaking it down a lot more than that. Evaluating how efficient TGE code is. Because it's like certain codes go faster than others, but I don't even know what he's talking about. I'll log in and I don't know. None of that. I need something a lot more basic than that. Says introduction to algorithms, but I don't feel like this is the introduction to algorithms. I don't know. Unless it's like that. I mean, is all that stuff like part of the coding and stuff? Obviously not part of Python. I don't see none of that in Python. I don't know. Yeah, this is that thing it was showing earlier. But I still don't know what any of this stuff is. Constant time operations take the same time regardless of input size, such as accessing an array index. Logarithmic time. Let me see if I can see a video of this.
We have got to the point where literally anybody can build a fully working app without knowing how to code. This is based.
Big O notation is a pretty big deal, and not just when it comes to coding interviews. When you write a piece of code, you want to have a rough idea of how efficient it's going to be. Sometimes it doesn't matter when the input size is small, but as the input size grows, the execution time of your algorithm is also going to grow, and you want to know how quickly, and that's where big O notation comes in. Now, it is a little bit mathematical, I'm not going to lie.
Ben, suppose you're on a game show, and you are given a chance to choose from 3 different doors.
But I'm going to show you it's really not so bad. I'm going to use a lot of pictures, diagrams, and examples. Let's start with the simple equation y equals 5x plus 2. The coefficient 5 determines the slope, the constant plus 2 determines the initial y-intercept. But in big O, we only care about how quickly the algorithm is going to grow as the input gets very large. For this equation, that means that we actually don't care about the constant plus 2, and we also don't care about the slope 5. The only thing we care about is that it grows linearly. And that's because if we have a different function, x squared, we know that x squared is going to pass any linear equation, regardless of the slope. Now, there's a little bit of calculus behind this that I won't get into, but also keep in mind that actually the rate of growth doesn't always tell the whole story, even though that's what big O is about. The input size does matter, and we are going to discuss that a bit. But before that, I wanted to quickly tell you guys about today's sponsor, Warp. Warp is a really powerful tool which interfaces as a terminal but has all the capabilities of state-of-the-art AI tools. It has two modes, terminal mode with constant time complexity. Constant time means that the algorithm does not grow with respect to the size of the input. So it doesn't matter whether the input is big or small. The total number of operations is always going to remain the same. A good example of this would be with the hash map data structure. Hash maps have an amortized time complexity that is constant for each operation: insert, delete, lookup, doesn't matter. And that's because these operations are implemented with a hash function. Doesn't matter how big the hash map is, an operation is always going to take the same amount of time, unless, of course, we are going to rehash the hash map, which is something we're not going to cover, and that's kind of why I say amortized time complexity, which basically means over a large amount of operations, the average time is going to be pretty efficient. It's going to be constant. If you want to learn more about that, you can check out the DSA for Beginners course on NeetCode.io. I teach it kind of the same way: video explanations, animations, written write-up, as well as some suggested problems for each lesson. Now, constant time doesn't always mean fast. In some cases, a constant time operation might be slower than one that is a linear time operation. For example, allocating a linked list node on heap memory is probably going to be more inefficient than reading through an array if it's a relatively small one. So do keep in mind that Big O doesn't always tell the whole story when it comes to real-world execution time. Logarithm...
Even this is like...
Constant time doesn't always mean fast. In some cases, a constant time operation might be slower than one that is a linear time operation. For example, allocating a linked list node on heap memory is probably going to be more inefficient than reading through an array if it's a relatively small one.
So, I mean, but Python doesn't use any of this stuff. Or I guess it does, but behind the scenes. This is what's confusing about this. I guess, like, before the Python, the other ones, like the more basic ones, I mean, you would have to know this stuff, like linked list and I don't know. I don't know how this comes from the coding that you're typing in.
Do keep in mind that Big O doesn't always tell the whole story when it comes to real-world execution time. Logarithmic time complexity is an interesting case. As the size of our input doubles, for example, from 8 all the way to 16, the number of operations will only increase by 1. Typically, when we talk about log, we mean log base 2. An example would be log base 2 of 8. By definition, it means what power would we have to raise 2 so that it would equal 8? In this case, it's 3. If you double it, log base 2 of 16, what power do you raise 2 to? Well, to the power of 4, and then you get 16. So you kind of see what I mean. Another way to look at it would be, how many times do you take a number like 16 and divide it by 2 such that it equals 1? This definition allows us to understand the classical example of binary search. Of course, binary search works by cutting our search space in half at...
Hello? Oh, yeah. Okay. Alright, I don't know if you're still there, man. I can't tell because it says concurrent 0 sometimes, but I guess I'm gonna have to get back to this later. I appreciate all the help, though.
Bye. Have a wonderful time.
You're on speakerphone.
I am on speaker.
Yeah.
Woohoo.
Well, it makes it sound like you're the one kicking me off.